So during the time it was accelerated by lunar. But if I'm stating that I plug in the big acceleration, it's not the velocity, it's not standard.
Are we live? 1 second.
True once and for all. The laws of Newton are not going to be modified.
Okay.
So you find the laws of Newton before you go to sleep. Wake up, you find them again.
All right. Let's check. Great. 3, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4, 5, 1, 2, 3, 4. Audio is the same as always. Let's check Windows audio. Mic is on. Okay. So I didn't touch anything and the audio is now good. Really strange. Okay. Okay, so what I wanted to do first, let's quiet down. Okay, so what do I want to do? So before we make this presentation explaining again, this revolutionary realization that Einstein pooped his pants and we no longer need to poop our pants. The fact that he assumed this constant speed of light for all observers is a superfluous assumption, because if you just assume ether as a liquid, then you get it from just wave mechanics. According to wave mechanics, everybody measures the speed of light, the speed of the wave as a constant, the same number, assuming that their clock is based on the waves. If it's a wave, if the clock is based on the medium through which they're moving, then they will always measure a constant, a cosmic or universal, call it whatever you want, speed of waves in the medium. So we have fantastic. Am I okay? So we have successfully reduced. This was, I think, the last and the first step in reducing Einstein theory of special relativity to absolutely nothing but wave mechanics. So the rest of Einstein special theory of relativity is correct, but it's nothing but wave mechanics. There's nothing, absolutely nothing special about Einstein theory of relativity, electromagnetic waves, whatever. Absolutely nonsensical. As long as you just assume a medium such as ether, and I suggest we go back to the ether. The luminiferous ether should be reintroduced in full force. There's no reason to play games, enough games, and that's enough. Enough said, as we say. So we will do this presentation again, just to make sure, just to drive the nail into the coffin again and beat the proverbial horse to death again, and whatever other idiomatic expression you want us to say for this to never come back. We should never speak of this issue again. Enough of the vacuum. I don't want to hear that word again in my life. There is no vacuum. There is an ether. If you don't like it, then tough luck. That is now a scientific, I don't want to say fact. I hate the word fact, but it is, the preferred scientific theory based on my definition of science. So Einstein gave us a magical thinking, non-scientific theory based on an assumption that is complete and utter nonsense. That's not the scientific method, and it's not even a mechanical theory. And as we know, it's not a classical theory. So it's garbage. It's not a theory. It's just pure garbage. So we can take Einstein. We can start from a mechanical ether, and then Einstein's special theory is valid. Everything he said is valid based on the ether. And the same goes for general relativity, because once we have the ether, I mean, I didn't even start from relativity. I started from an explanation why the apple falls towards the earth. That is my basically origin. I started from trying to understand gravity once and for all, and I derived a velocity field vector gravitational equation from Newton, which is a degenerate case of Einstein. So it's basically Einstein, his field equations. That gave me a fluid flow that is dragging us and sucking us into the earth and sucking the apple and sucking the moon, but it's a fluid. That fluid, there was no room for particles, so I realized, well, everything is a wave, as is said in quantum field theory. So everything is a wave, and that's it. Now we have general relativity that works directly with quantum mechanics, absolutely no issue. I don't know why everybody's losing their minds. Now, you could say that general relativity, you could say that I don't know, I mean, why can't you say general relativity is a good explanation for any subatomical particle slash wave? So you could say, well, everything is a wave. Well, a neutron is composed of, I guess, waving particles, but you can look at the neutron as a particle and you can visualize the ether flowing into the neutron. I don't see the problem with that. And anyway, I need to come back. I've already made plenty of what do you call it? Presentations where I explained this theory. So I don't see an issue. I don't know. I never understood anyone who couldn't figure out why Einstein general relativity fits perfectly in with the microscopic quantum mechanics. Anyway, enough said. The next step is I want to just review, has anyone made this proof? Has anyone gone through this proof that the speed of light is a constant if you just assume that your clock ticks based on a mechanism based on the waves themselves, such as my rubber ducky. And by the way, someone should build this mechanical rubber ducky and sell it. This is how you can teach relativity. At least special relativity is easily now taught in the bathtub. Babies can now play with special relativity. It's completely mechanical. Completely mechanical. Someone please build this mechanical rubber ducky and sell it. Enjoy the profits. You know, you can credit me and send me some cash. I'm not going to object. I cannot take, you cannot write a patent because I already made the information public. But if you build it and you want to credit me and give me money, and I'll give you my endorsement if it works properly, then we can move ahead and create a business out of that. And this can be taught in classes in high school. This could be the next revolution, because I'm taking Einstein and I'm reducing Einstein to his proper size from a god to a dummy dum dum like me. I'm a dummy dum dum. Okay, but he's not a god. He made mistakes. Special relativity, general relativity, these are all mistakes. He didn't understand things properly. Now it's time to fix it. Stop worshiping this guy. Don't worship me. Don't worship him. Stop worshiping and quit your job. You're not worthy of being a scientist. If you didn't figure this out, it took me literally 2 weeks to figure it out. So if you haven't figured it out in over 100 years, you should quit your job, give your money back, give the money back to the university, whoever you took money from, give it back, go get a real job. Why don't you go clean the streets a little bit? Anyway, let's continue. So I wanted to watch some lectures. I don't know. I'm still open minded. Has anyone ever figured this out? It's just too ridiculous for no one to have ever figured it out. So let me just make a copy of the link to our Discord. You can join me in my Discord and we can laugh together and share experiences. Anyway, what I wanted to do now is first of all check the audio. Mic check, mic check, check, mic check is good. So we can let me close some windows. What is this? Windows relativity concept, Lorentz gamma. Okay, I think we're done with Lorentz for now. Thank you, Dialect, for your video. Good video. How many subscribers? Still 176. What was it this morning? 176. We need to celebrate each and every new subscriber. All right. So the next step is, let me close some windows. This is Einstein's paper. We're done with that. And Annus Mirabilis, we don't need. Let me just close some nonsense. Oh, this is the one? Okay. This is the one I was looking at. We read this one. Let me close. Okay, we need to listen to. I know there is, I think, at least 2 courses online of special relativity. So let me go. Let me grab the one that I'm listening to right now. This one, Introduction to Relativity.
You'll get the same laws. That's the claim. And I hope you understand that all the mechanical things you see in the world around you just come from F equals ma. We have seen projectiles and collision of billiard balls and rockets.
This is utter nonsense. Everything he's saying is utter nonsense because he's treating relativity as a magical theory. The laws of nature remain constant for all observers. Yeah, that, what do you want me to say? You didn't say this when you taught electricity and magnetism for some reason. You didn't teach it when you were teaching, I don't know, rotational inertia, whatever. You didn't say, "Oh, the laws must be." No, why do you say it when you teach relativity? It's ridiculous. This is magic. This is not science. Stop it.
Rockets. They're all Newtonian.
Take this course offline. Let me check if he says. Let me go full speed. Let me check if he says anything even remotely similar to my proposition.
In mechanics. So to say that things will look the same is to say the laws of Newton that you will deduce before and after waking up will be the same. So let's show that. When you show that, you're really done with it once and for all. So let's do the following. Here is the x-axis, and here is my frame of reference.
Of course, they all teach relativity with trains. That is nonsensical. That's not how you should teach relativity. It's a theory of waves. Stop confusing everyone. It's a theory of waves. It's just wave mechanics.
This is my x-axis. Let's call this the origin. The frame goes to negative and positive x values. Pick some object sitting at the point x. Now, we are going to first define the notion of an event. An event is something that happens at a certain place at a certain time. That's called an event.
This is such nonsense. You should teach it as waves and explain, just like I did. That's the way you should teach it.
For example, if there's a little firecracker going off somewhere at some time, the x is where it happened and the t is when it happened. So this is space-time. Once again, space-time does not require.
There's no time. Stop saying time. There's only the clicking of a clock. There's no time. Stop saying time.
Einstein coming at all. We've known for thousands of years.
Stop mentioning Einstein. He had nothing to say. This is just wave mechanics.
That if you want to set up a meeting with somebody, you got to say where and you got to say when, and things do happen in space-time. The fact that you need
space-time. I'm going to kill myself.
T, or if you're living.
Say space-time one more time. Don't say time. Say click, tick, clock tick.
These spatial dimensions, the fact that you need x, y, z, and t, is not new. That is not the revolution.
Don't say time. Say the ticking. The ticking, tick, tock, tick. It's a mechanical ticking of a mechanical clock that works on the basis of the waves of the medium in which the clock is moving. That's it. That is the theory of relativity. There's no theory and there's no relativity. It's just wave mechanics. That's all it is.
That Einstein created, the fact that you need four.
And thank you, Dialect, for opening my eyes.
For coordinates to label an event is nothing new.
The first time I saw that video by Dialect, I was like, exactly. Finally, someone, because I was thinking about this for such a long time, and then finally they said it. Finally,
What he did that is new will be clear later.
they taught me the math, and it's really straightforward. And by the way, I don't need any math. What I presented in the previous presentation is not. There's no math. It's very straightforward. There's no calculation. You don't need gamma. You don't need. You just need to understand what's given and what we're asking. It's simple wave mechanics.
So everyone understand what
The speed of a wave as measured by any observer is a constant as long as the measurement is done mechanically by a clock that is based on the ticking, that is based on the waves, that are based on the media in which the clock is moving. Done and done.
an event means. Okay, event is something that happens, and to say exactly when and when it happened in our world of one dimension.
This is so confusing. This has nothing to do with anything, just complete nonsense.
We give it an x and we give it a t. Now that's me, and I'm going to give my frame of reference the name s.
Oh my god, this is so confusing. Completely useless.
Turns out s is not just based on my name. This is canonical name for two observers. One is called s, and one is called s prime. So s prime, let's say, is you. So your frame of reference is going to be taken to be sliding relative to mine. So I don't know how to draw this. Let's draw a y-axis here. We don't really deal with the y-coordinate, but just to give you a
And by the way, he didn't say the postulate in this lecture that the speed of light is a constant as observed by all moving observers. I can't wait for him to say it and say, it's a postulate. We don't know. I can't wait for him to say this.
feeling. This is my y-axis.
Unless he's going to say, well, I can prove it.
Next axis, this is my origin. Y is not going to play a big role. Now you're sliding this way to the right, and your speed or velocity is always denoted by u. So some number of meters per second, you're zooming to the right at some speed u. So imagine now, you're going past me. At some instant, I'm sitting here at the origin of coordinates.
So confusing.
You cross me.
I don't even understand what he's talking about.
And then a little later, you're somewhere there. So that's your y.
Why not show a bathtub like I did with two rubber duckies and start with first one rubber ducky and then you can move to two rubber duckies?
Prime axis, that's your origin. And the same event, you say has a coordinate x prime.
Oh my god, this is so confusing.
We arrange it so that when you zoom past me, you set your clock to 0, and I set my clock to 0. When you want to set the clock to 0, it's completely arbitrary. So we will decide, right when you pass me, I'm at the origin of my coordinates, you're at the origin of your coordinates. Right when you pass me, we'll click our stopwatches, and we will set that time to 0.
And how do these clocks work?
So here's an event. You and I crossed. What are the coordinates for the event? According to me, that event occurred at x equal to 0, and the time was chosen to be 0. According to you, your origin was also on top of my origin, so x prime was 0, and the time is just the time. Everybody has a single time. That time is called 0. That is one event. We made the coordinate of the event 0, 0 for both you and me. It is 0 in space because my origin crossed your origin. The crossing took place at my origin. That's why my x is 0. Took place at your origin. That's why your x prime is 0. And the common time we chose to be 0 by convention. Then we want a second event. So let's say the second event is some firecracker going off here. Here's something I should explain that I used to forget in the previous years. When I say I am moving, I imagine I'm part of a huge team of people who are all moving with me. So I got agents all over the x-axis who are my eyes and ears. They're looking out for me. So even though I'm here, there's a firecracker exploding here, my guys will tell me. And you are carrying your own agents. Let's say at every point X you have a reporter. X equal to 1, 2, 3, 4. There are people sitting and watching. So when I say I see something, I really mean me and my buddies all traveling the same train at the same speed, all over space, taking notes on what's happening. We'll pull out information later, but we know this explosion took place here. I would simplify by saying I know an explosion took place here at location X at time t. So this is our crossing. This event is when we crossed. Then there is the firecracker. For firecracker, I have to give some events. I say it took place at location X at time t. What do you say? You measure the distance from your origin. You call it an x prime. The time is still t. In Newtonian mechanics, the time is just the time. How many seconds have passed is the same for everybody. The question is, what is the relation between x prime and x? That's what we want to think about. So you guys should think before I write down the answer. What's the relation of x prime to x? Well, this event took place at time t. So I know that your origin is to the right by an amount u times t. So the distance from your origin for this event, I maintain is x prime, is x minus ut.
X minus ut. Let me see. So confusing. Okay, you are moving at u, and he's stationary? Again with the endless messages? Okay, whatever. I don't know. It doesn't matter.
Event, I maintain is x prime, is x minus ut.
I never followed all these derivations. They're just so confusing. Oh my god, so confusing. The first time I understood a derivation that I remember is dialect with the sound waves. So straightforward. At this point, I don't know what's going on. I don't know where's his train, your train, who's moving, who's not, who's zooming, what's zooming. Who knows? It's the most confusing diagram in the world. So I'm assuming I'm still here, he is still here, and you is zooming by. So at time t, this is the new t. Should be t2 because this is t equals 0. This is t. It doesn't make any sense. T equals 0 and this is t. You should say t1 equals 0 and t2 equals some t, whatever. Like, I don't know. Give it a maybe, I don't, whatever. So ut is the distance that you covered because your velocity is u. So your origin, y doesn't matter. So x prime. So you are located. So x prime. What is x prime? This distance. What is this distance? This is your train. I don't even know what this is. What is x prime? I don't know what it is. X prime is equal to x minus ut. What is x prime? It's a distance of where, I guess, the firecracker blew up at x at my time t. So this distance, what is, I don't know what this distance is. Your origin now is at ut, and x took place at where you were. I don't know. I honestly don't know. I don't know. So this distance, well, this is ut and this is x. Okay. So this, but what does this distance signify? So you moved ut and it took place at x. Okay. So you're here. You're at ut. So what is the distance x that you're seeing? You're seeing x prime, that is x, according to me, minus ut according to me. So according to me, your x prime, whatever that is. What is x prime? I don't know what x prime is. What are you trying to say? What is x prime? Why be so confusing? What is x prime? What do you want to say about x prime? I don't get it. I hate these confusing courses. What a waste of time. Okay, let's hear.
I'm sitting here at the origin of coordinates. You cross me, and then a little later, you're somewhere there. So that's your y prime axis. That's your origin. And the same event, you say has a coordinate x prime. We arrange it so that.
So according to you, okay, so according to me, the event occurred at x. According to you, the event occurs at x prime. So this is the discussion of simultaneous event. There's an event that I think it happened at x. You, according to me, you must think it happened, according to you, at x prime. Okay. Where is x prime? What is the distance x prime? It's my x minus my ut, where u is the velocity I measure that you have. How do I know your velocity? I don't know. Who knows? That's an assumption.
That when you zoom past
So this is incomplete.
me, you set your clock to 0, and I set my clock to 0. When you want to set the clock to 0, it's completely arbitrary. So we will decide, right when you pass me, I'm at the origin of my coordinates, you're at the origin of your coordinates, right? When you pass
That's fine, but how do you know the speed? How do I know your speed? So I need to measure your velocity. So I'm measuring, so your velocity is u in my frame of reference, okay?
we'll click our stopwatches, and we will set the time to 0.
Why do you call this you and me? Why not call it person A, person B? Like B or Mr. Prime and non-prime. Give it a normal name, not me and you. Who's me and you? Who? Because when you say you mean me. So who is me and you? Jesus.
0.
It's like how to teach relativity so that it ends up being the most confusing thing in the universe for no reason. Why would you make it so confusing? I don't know. Something is wrong with these people.
So here's an event. You and I crossed. What are the coordinates for the event? According to me, that event occurred at x equal to 0, and the time was chosen to be 0.
How could you say t?
According to you, your origin was also on top of my origin. So x prime was 0, and the time is just the time. Everybody has single time. That time is called 0. That is one event. We made the coordinate of the event 0, 0 for both you and me. It is 0 in space because my origin crossed your origin. That crossing took place at my origin. That's why my x is 0. Because of your origin, that's why your x prime is 0. And the common time we chose to be 0 by convention. Then we want a second event. So let's say the second event is some firecracker going off here. Here's something I should explain that I used to forget in the previous years. When I say I am moving, I imagine I'm part of a huge team of people who are all moving with me. So I got agents all over the x-axis who are my eyes and ears. They're looking out for me. So even though I'm here, there's a firecracker exploding here, my guys will tell me. And you are carrying your own agents. Let's say at every point X, you have a reporter. X equal 1, 2, 3, 4. There are people sitting and watching. So when I say I see something,
And he's so confusing. What is he talking about? My people, your people. What are you talking about? So I guess I don't know who is I, person A, the non-prime person, has people all over the x-axis. And you have people all over the x-prime axis. So you see everything. You're always seeing everything on your axis. Okay.
I really mean me and my buddies all traveling the same train at the same speed, all over space, taking notes on what's happening. We'll pull out information later, but we know this explosion took place here. I would simplify it by saying, I know an explosion took place here at location X at time T. So this is our crossing.
Let me check messages. Sorry, 1 second. Let me just respond.
This event is when we crossed. Then there is the firecracker. For firecracker, I have to give some events. I say it took place at location X at time T. What do you say? You measure the distance from your origin. You call it some X prime. The time is still T. In Newtonian mechanics, the time is just
Let me see. Message.
time. How many seconds have passed is the same for everybody. The question is, what is the relation between X prime and X? That's what we want to think about. So you guys should think before I write down the answer. What's the relation of X prime to X? Well, this event took place at time T. So I know that your origin is to the right by an amount U times T.
T. Everything is T. Everything happened at T. Call it T1, T event, T something, not T. This is the time of the event. At the time of the event, when the event happened at X, or according to you at X prime, you were obviously at UT. I measured your speed U, and the time of the event is T. So, yeah. So, okay.
So the distance from your origin for this event, I maintain is X prime, is X minus.
So the distance from your origin to the event, X prime, in my coordinate system is X minus UT.
UT. So the distance from your origin for this event, I maintain is X prime, is X minus UT.
I maintain?
Again, I want all
So confusing.
of you to follow everything. These are all simple notions.
Yeah, very, very, very simple. Make it more confusing and say that it's even more simple. Ridiculous. And people pay money for this. It's very sad.
Our origin coincided at 0 time, but the event occurs at time T. Therefore, in a sense, you're rushing towards the event. You've gone a distance UT. Therefore, the distance from your origin to the event will be less than mine by this amount UT.
So I maintain it's X, but you've moved forward. So for you, it's X prime, which is just my X minus your UT or my UT. Okay, whatever.
This is the law of transformation of coordinates in Newtonian mechanics. If you have an event, which occurs at, if you want formally, you can define a time T prime for the primed observer. It goes without saying that T prime and T are the same. There's no notion of time for me and time for you.
That's the most ridiculous thing in the world. You mean the ticking of a clock? Well, I mean, if you would have explained that this is just wave mechanics, everybody would have understood this a million years ago and would have said, okay, who cares? The only reason to care is to realize that everything in the universe, the only thing to care about, the only thing that really the only revelation Einstein had is that our internal clocks are light based. Where he got this from, I don't know. That I don't know where he got it from. And that's what he said. We feel all of the laws of nature feel the same. I mean, that's true in any. That's true because obviously because of wave mechanics. but that our observation is light-based. I don't know where he got this notion from. That every particle in our body is as fast as light. Really strange. Okay.
There's universal time in Newtonian mechanics. It just runs. We can call something a zero. Once we have
Stop saying time. Talk about there's no such thing as time. There's only the tick tock, ticking of a mechanical clock. Define the mechanism, everything will be clear. Stop saying time. There's no time. Time is measured as the ticking of a mechanical clock. Stop saying time.
agreed.
Or define time as the ticking of a mechanical clock.
If you say you and I met at t equal to 0, an explosion took place 5 seconds after our meeting, it's going to be 5 seconds after a meeting for me, and it's going to be 5 seconds after a meeting for you. The time difference between two events is the same for all people. This is called the Galilean transformation.
So is it Newtonian or Galilean?
What are the consequences of Galilean transformation? Well, let's look at the fact that x prime is x minus ut. Remember, everything is varying with time. So x prime is a function of time, and x is a function of time if you're watching a moving particle. Suppose this firecracker is not just one event, but it's a moving object. Let's give the object some speed. It's moving to the right. Then the velocity, according to me, I'm going to call v as dx dt. Is the velocity. Let's just call it a...
Make it more confusing. Okay, so this x is actually now moving, so it's no longer just static x. It's x of t. So its velocity, the event now is moving at dx dt.
bullet. According to S, then W is the standard name.
Bullet.
It's the velocity of the bullet, according to
What
S
do you
prime.
mean for S? Okay, S is my frame of reference, my space. S prime is yours. So I measure the velocity of the bullet, dx dt. You measure the velocity W of the bullet, dx prime dt in your space, okay?
So what I've done is I first took one event, and I gave it some coordinates, and I told you how to transform the coordinate from one person to the other person. But now take that point X not to be a fixed location, but a moving object. So as a function of time, that body is moving. Then its velocity at any time is dx prime dt, according to you. That is the dx dt, according to me, minus the derivative of this, which is u. Now, does that make sense?
Yeah.
You should agree with.
So in your frame of reference, the velocity of the bullet is W, and W is v minus u. Now I measure the speed of the bullet as v, which is dx dt, and minus. So v, the speed of the bullet is dx dt. W is dx prime dt. This is x prime. So W is dx prime dt. Dx prime dt is dx dt, which is v minus the the dt of this, which is u. So what does this mean? What is W? W is how you measure. This is how you measure the speed of the bullet. If I measure it as v, then you must measure the speed of the bullet as how I measure, obviously, the speed of the bullet, but minus your speed in my frame of reference. That's how you measure in my frame of reference, because V and U are in my frame of reference, are both in S. So I know that you measure the speed as such, as V minus U, in my frame of reference. You measure it as W, and W is V minus U, okay?
Common sense. For example, if the bullet's going at 600 miles per hour to the right, that is 600.
Right. If the bullet is going at 600 miles to the right, according to S, then let's assume U is 200. So it's 600 minus 200. So it's 400. So
For me.
W.
And you are going to the right in your train at 200 miles per hour. You should measure the bullet speed to be reduced by 200. And you should get
This is 600 minus 2. This is 400.
400. That's all it means. The two people will disagree on the velocity of the bullet because they're moving relative to each other. This is the way you will add velocities.
That's particles, but that's not waves.
But let's look at the acceleration.
But light is a wave, and everything we observe in reality is through waves, waves of light. So let's discuss this in wave mechanics and not in particle mechanics.
W dt is going to be dv dt minus
W dt. Well, W is how you appreciate the velocity of the bullet in your frame of reference. So, well, is the that should be zero. The VDT, I mean, I don't know, it should be zero, no?
and it's 0 because u is a constant.
That's not zero, that's the empty set. Oh my God.
That means you and I agree on the acceleration of the body. We disagree on where it is. We disagree on how fast the bullet's moving, but we agree on the acceleration of the body because all I've done is add a constant velocity to everything you see. Therefore, if according to you the velocity of the body is not changing, according to me the velocity of the body is not changing. Because we both, the constant I added will drop out of the difference. Or if the body has an acceleration, we'll both get the same answer for the acceleration. So that is the common acceleration A. So if you like, A prime is the same as A. So the acceleration of bodies doesn't change when you go from one frame of reference to another one going at constant speed. All right, so let's look at F equals ma, which is m d2x over dt squared is equal to some force on the body.
Okay, this is F equals ma, okay?
And you look
So F equals m, the second derivative of x. X is the location of m.
at the body and you say d2x prime over dt squared is the force on your body.
Oh my God, why is he confusing this so much? And he's hiding what he's writing. So it should also be the same in your frame of reference.
First, I want to convince you. We wanted to see that the left-hand sides are equal because the acceleration is the same. Then I want to
Well, there's no force on the bullet, so it's zero.
convince you the right-hand sides are also going to be equal. I can take many examples, but eventually you'll get the point. Let us not consider one body, but let's consider two bodies. Two bodies are feeling a certain force due to, say, gravitation.
What?
And gravitation is, of course, a force in 3 dimensions, but let's write the force in just 1 dimension. And let's say the force of gravity.
What is he talking
is 1 over
about?
x1 minus x2, force on
Why is he involving gravity in this discussion?
1 due to 2, and the force on 2 due to 1 will be minus of 1 over x1 minus x2. The real forces are R1, the separation in 3 dimensions, but this is a fictitious force. I want to call it gravity. It is any force that depends on the coordinates of the two particles. So I will say m1 d2x1 over dt squared is 1 over x1 minus x2. And m2 d2x2 over dt squared is minus 1 over x1 minus. I forgot.
Okay, it's some force that depends on the distance, whatever. Okay, 1 over the distance. Gravity depends on the square of the distance, but fine.
So here are two bodies. They feel a force for each other, and I've discovered what the force is 1 over x1 minus x2. I don't care if it's 1 over x1 minus x2 or x1 minus x2 squared. That's not important. What's important is it depends on x1 minus x2. You come along and you study the same two masses. What will you say is happening? You will say m1 d2x1 prime over dt squared is equal to 1 over x1 prime minus x2 prime. Maybe let me do it a little better. I can tell you what you will see. Given this is what I see, I can tell you what you will see. Let's do that in our head. We know that the acceleration is the same for any mass, so I'm going to write this thing as m of d x1 prime over dt squared. In other words, the acceleration, according to me, is the same as the acceleration according to you. Then I'm also going to write the right-hand side as x1 prime minus x2 prime. Now, do you understand that? If there are two bodies feeling a force, if you see it from a moving train, the distance between the two bodies is the same for you and me. Because x1 prime is x minus ut, x2 prime is x2 minus ut. Take the difference. The difference between the location of the particles is the same for you and me. Acceleration is the same. Mass is postulated to be the same. So I know that you will get the same law that I get. You will get F equals ma. Your acceleration will be the same as mine. The force you attribute between two bodies will also be the same.
I'm not getting anything. I'm wasting time because I want to still develop more stuff in under my assumptions, and this is a waste of time. I just want to hear if he ever says the postulate.
That is why I know that you will also deduce the same Newtonian laws that I will. You can also see it differently. If I woke up from my nap and I'm now in a moving train and I examine the world around me, I'm going to get the same F equals ma. Because as seen by a person on the ground, the masses obey F equals ma. I'm in this moving train now, but I have the same acceleration for each mass and I have the same force. So if you want to complete the second equation, m2 d2x2 prime over dt squared will be minus 1 over x1 prime minus x2 prime. Like this is a little difficult.
Not even halfway done with this introduction to relativity. God help us.
I'm telling you that if I deduce F equals ma, and the F depends on the separation between the particles.
How can you confuse something so simple so much? You got to be a genius. Only a genius can make such a mess out of something so simple.
Then I'm sure that you will find the same laws of motion because the acceleration is the same that I get because we have seen A prime is the same as A, and the force will also be the same because the force depends on the separation between particles, and that doesn't depend on.
Okay, no one sees. No one is accelerating, so the bullet is not accelerating. So there's no force. I don't know what he's talking about.
Which train you're in, or it's not affected by adding a constant velocity to the frame of reference. So if you like, this is the way you prove in Newtonian mechanics the principle of relativity.
What?
So not only is it
This is such a nightmare.
You observe by going on trains and whatnot, you can actually show that this is the reason everything looks the same. In other words, if the train was at rest on the platform and you and I were comparing notes and we both find F equals ma, I go to sleep and I'm waking up with the train going at a constant speed. If you can look through the window and look at the objects in my train, you will say they obey F equals ma because nothing has happened to you. But you will predict I will also say F equals ma because if you see an acceleration, I will see the same acceleration. If you see a distance between two masses to be 1 meter, I will also think.
What is given? What is not given? I don't know. I don't know what he's asking. I don't know.
It's 1 meter. If the force is 1 over the square of the distance, we'll agree on the force, we'll agree on the acceleration, we'll agree on everything. And once you prove an F equals ma is valid, it follows that every mechanical phenomenon will behave the same way. That's the reason things behave the same.
Why would it not? I mean, it's just wave mechanics. Why would you have to prove anything? It's just wave mechanics. It's a bathtub with a rubber ducky. What's so confusing?
Yep. Pardon me?
It reminds me of how religions complicate everything. This is like a cult.
If the rule failed in the other frame,
Like my intuition is Einstein would have watched this and would have said, what the heck are you talking about?
yeah, suppose hypothetically that happened. Then it would mean that when you wake up in the train, you will look at the world around you, it will look different. Because F is no longer ma, you'll conclude when I went to sleep, it was F equals ma. When I got up, F is not equal to ma, the train is moving. So you have to conclude that uniform velocity makes detectable changes. And if you look outside the train, to the other train's going backwards, you cannot no longer say, you're going the other way, I'm not moving, because the other person will say, hey, F equals ma works for me. It doesn't work for you. So you're the guy who's moving. So you've lost the equal status with other inertial observers because those for whom F equals ma work will say they're not moving, and for you, it doesn't work. So you'll have to conceal your movement. So uniform velocity, if it makes perceptible changes, can no longer be considered as relative. It's absolute. And if you and I find each other moving, there may be a real sense in which I'm at rest and you're moving, because for me, F equals ma works, and for you, it doesn't. But that's not what happens. In real life, you find it works for both, and we say either of us can maintain we're not moving. So now you got to fast forward to about 300 years. This goes on, no problem with this principle of relativity. And 300 years later, people have discovered electricity and magnetism, and electromagnetic waves, which they identify as light. And then it was discovered that what you and I call light is just electric and magnetic fields traveling in space.
Let's see if he messes up Michelson and Morley. Because Einstein, I don't even know. At this point, actually, I don't know because Einstein seems to reference. I don't think Einstein remembered during 1950 that he actually referenced Michelson and Morley implicitly. Because he did. He did reference Michelson and Morley implicitly. Where's the velocity? Assign velocity to a point, empty space, blah, 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 blah. Where's that nonsense? Okay, examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relative to the light medium. This is literally Michelson and Morley. Suggests that the phenomena of electrodynamics as well as of mechanics possesses no properties corresponding to the idea of absolute rest, which is the, what do you call it? The ether. They suggest rather that, as has already been shown to the first order of small quantities, the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. 1. What is 1? What is 1? 1. The preceding memoir by Lorentz was not at this time known to the author. What preceding memoir by Lorentz? What? What's going on? It says here Einstein. June 30th, 1905. What is going on? The preceding? I don't know. I don't know what's going on. I don't care. Let's continue with this nonsense.
You don't have to know what electromagnetic fields are right now. They're some measurable phenomenon. They're like waves. And the waves have a certain velocity.
Oh, they're like waves that have a velocity. Oh.
Actually calculated. The velocity is this famous number 3 times 10 to the 8 meters per second. And the question was, for whom is this the velocity? Then, for example, you can do a calculation of waves on a string, something we'll be able to do in our course. Waves on a string will be some answer that depends on the tension on the string and the mass density of the string. And that's the velocity seen by a person for whom the string is at rest. Or if you calculate the waves of sound in this room, and I talk to you, you hear me slightly later, the time it takes to travel is the velocity of sound in this room. That is calculated with respect to the air in this room, because the waves travel in the air. In fact, the fact that all of us are sitting on the planet, which itself is moving at whatever 1100 miles per second, doesn't matter, because the air is being carried along. So even if the Earth came to a sudden halt, as far as the velocity of sound in this room is concerned, it won't matter, because we're carrying the medium with us. So people wanted to know, what is the medium which carries the waves of light, electromagnetic waves? First of all,
I don't think they wanted to know. They just wanted to measure it, measure the speed. They assumed it's the ether.
medium is everywhere because, but how do we know it's everywhere? Anybody tell me?
Because we see the light from distant galaxies.
Yes? Right, it travels to the vacuum of space. We can see the sun, we can see the stars. So we know the medium is everywhere.
Okay, this is a very important message. Okay, this was very important for me to get this message because this has to do with my favorite, most beautiful chick. So I saw her, and I think I can get her back, but it's going to take some effort. But I'm built for that. Let's continue. Let's check the audio. Oh, 3 people watching. Very nice. Okay, let me just check the audio. Mic check. Mic check. Mic check. Mic check. Mic check. Mic check. Yeah, check. Mic check is good. Anyone who wants to join me? Oh, 2 people. If you want to join me in the Discord, you're welcome. I'm waiting. We can have a discussion. This is really important. So we're just looking for any reference. He's about to make a reference to the assumption of the constant speed of light as measured by all moving observers. This is very important. Will he say, will he prove it, or will he just assert it?
Then you can sort of ask, how dense is the medium?
So he is in trouble because if he's teaching Einstein's relativity, then he has to say it's a postulate, it's an assumption. And if he's able to prove it, then he has to say Einstein didn't understand it. So he's contradicting Einstein, who is a god. You're not allowed to contradict God. So either way, he is stuck between a rock and a hard place, as they say.
Turns out that denser the medium, more rapidly signals travel in most of the things that we know. For example, when we look at waves and sound, and when we look at sound,
He's talking about the properties of the ether that will determine the speed of the waves through the ether, namely the light waves.
waves in a solid or an iron, you find that the very dense material velocity is very high. So this medium, which is called ether, would have to be very, very dense to support waves at this incredible velocity. But then planets are moving through this medium.
That's exactly it. It's very dense. That's why there's no particles. That's why there's only waves.
Years and years and years and not slowing down. It's a very peculiar medium. But it has to be everywhere. So we're all immersed in this medium because we're able to send light signals to different parts of the universe.
Yep.
And the question is, how fast is the Earth moving relative to this medium? You understand? This medium is all.
Well, that's an assumption. But that's because you didn't start from gravity. If you start from gravity, you have to believe that there is an ether, again, very dense, grabbing the moon and grabbing the galaxies. So we're immersed in this very stiff, very rigid fluid. So you would end up believing that it's a stiff. What was he saying just before?
How fast is the Earth moving relative to this medium?
Then you would know that this medium is flowing into Earth and not that the Earth is moving through it. The Earth is also a little bit moving through it, but it's mostly flowing into Earth, right through us, dragging us into the Earth, dragging the apple into the Earth.
You understand? This medium is all.
Let me check what's going on here. Okay, everything is fine.
Pervasive. We know that we can see the stars, so it's going all the way up to the stars and beyond. And we are immersed in this. We are drifting around in space. What is our speed relative to the medium? That's the question that was.
There's like he's assuming that it's and so did Michelson and Morley, that it's like we're immersed in this nonsensical liquid. Like if you'd assume that it's moving, you would get different speeds of light and different stars would look weird. Like if it's just a nonsensical fluid, like you could say no, it's a solid, it's a very stiff liquid that all the galaxies are moving through. Anyway, as I said, I started from gravity, and that's when I realized that it must be there. So lucky me.
Was asked. Well, to find the speed relative to the medium, you calculate the velocity in the medium by Maxwell's theory. So here's the medium in which waves travel at a certain speed. This is planet Earth going around the sun. At some instant, you will have a certain velocity with respect to ether. And therefore, the velocity of light as seen by you will be modified from c to c minus v.
This is not Einstein relativity. It is. Right. We just saw that it is. They suggest rather, right? This is Einstein. Einstein together with the unsuccessful, right? Here it is. The unsuccessful attempts to discover any motion of the Earth relatively to the light medium. This is the luminiferous ether. Okay.
In particular, suppose the waves are traveling to the right in ether, and let me draw it this way: the Earth is going at this instant at a speed v. We expect the speed to be c minus v, because part of the speed is neutralized.
So if we so obviously the speed of what?
Right this way: the Earth is going at this instant at a speed v. We expect
If the Earth is moving v to the right, and the ether is moving, I don't know, to the right also. So I would say that what should be the speed of light? It should be lower. The Earth is moving at v, so ultimately it's going to move at the speed. So the speed of light through the ether is c. The ether is moving to the right. No, the ether is standing still. This arrow is the speed of light c. This is Earth moving v relative to the ether. So of course this is c and this is v. So we would notice that this is like a duck. This is a duck moving to the right in the water. The rubber ducky moving to the right in the water. It looks like it should measure v. Sorry, at v, it looks like it should measure the speed of the waves. Right, at this point when I was listening to this many years ago, at this point this made no sense because I was like, but it's a wave. Why are you adding and subtracting? It's a wave. Yeah. No, if the rubber ducky, no, he's right. If the rubber ducky is moving to the right at v, but the question is, how are you measuring this? How do you measure the speed of light? So he's like, how is the ducky measuring the speed of light? How are we measuring the speed of light? So we have these experiments that I forgot the name of the guy who measured the speed of light with the rotation and the slits. So he measured the speed of light. So you measure. Should you measure the speed of light as slower? Well, if you're moving through the medium, so the rubber, I don't know. I mean, this. So I don't know. I don't know. I need to know what you mean by this. So again, if you're running the experiment like they used to, and you're measuring the speed of light, well, it depends in which direction. The speed of light in this direction should be what? Slower or faster? Should be slower, I think. Right? To the right, it should be slower. To the left, it should be faster. And up and down, it should be impacted because of the effect of the waves. I don't know. I mean, so I'm assuming that the test for the speed, the assumption is that it's not impacted, right? The clock that is being used is not impacted because we didn't think at this point that the clock is actually being impacted by the motion. We're assuming that the clock is not impacted. That was the assumption. The clock is not impacted, so the speed should be different in different directions. Oh, but they were right. Wait, what about the interferometer? The interferometer, that's it. The interferometer doesn't depend on the motion of particles. The interferometer is pure light. interfering with itself, horizontal versus vertical. So the interferometer, a very big, like we've already discussed, like the size of the interferometer, but an accurate enough, a gamma ray interferometer with multiple mirrors, and it's really sensitive, a really sensitive. But they knew the speed. They knew that they're hopeless. They should have predicted a null result because of the primitiveness of their equipment. Anyway, that's an interferometer. So the interferometer, Carlos, works. What works? What are you talking about? Works. So the interferometer is one thing, but the speed of light detection. I think we saw movies or videos on YouTube how the speed of light. So assuming this that the speed of the moving circle thing with the slits is not impacted by the motion through the ether, then if you move with the ether, if you test light in that direction, it should be different than that direction. Like that should be slower and slower and slower. That should be faster. And these up and down should be less impacted, but also slower. So they should have expected results of different speeds of light. But why did they use an interferometer? Why not just measure the speed of light? I mean, the interferometer is genius because it has no moving parts. It doesn't depend on moving parts. It should have worked. If they would have done the calculations properly, they would have discovered that it's too inaccurate for the motion of Earth through, whatever speed. I don't even know what speed you're assuming. The galaxy through the ether. What is moving? What is your assumption? I don't know what numbers are you using? Because in my calculation, anyway, if they should have gotten a null result, knowing what I know. But anyway, let's continue. Because we already discussed this enough. I don't want to rehash it.
Because part of the speed is neutralized, right? From c to c minus v. In which waves travel at a certain speed.
Okay, he's not explaining this enough. So it depends in which direction you're doing the test.
This is planet Earth going around the sun. At some instant, you will have a certain velocity with respect to ether. And therefore, the velocity of light as seen by you will be modified from c to c minus v. In particular, suppose the waves are traveling to the right in ether. And let me draw it this way. The Earth is going at this instant at a speed v. We expect the speed to be c minus v.
So confusing. No, it depends on which direction you're conducting the speed of light test in. If you're conducting it in the direction of the motion of the Earth, I think you're right. If you're conducting it in the opposite direction, then it's c plus v. No. If you're conducting it this way, then it's going to slow down. But what about if you're conducting the test to the left? I don't know. This is so confusing. What happens if you run the test to the left? To the right, you can say it slows down. But to the left, doesn't it speed up? Isn't it c plus v? Right? This is the direction of the test. So if you're conducting the test with Earth, that's the slowest. If you're conducting the test opposite, that's the fastest. That's c plus v. So it's like you should get different results as you rotate. No one has done this experiment. You should have done the test of the speed of light. Let me show you the test of the speed of light. And he's not explaining it. He's on top of everything. I don't want to say that he's a terrible explainer, but there's so much more details, but he has no time. Instead of, let's conduct the experiment. Let's conduct the experiment right now in class. How about that? How difficult is that? It's a simple experiment. They used a candle. Let me show you. The speed of light. I love it when I watch a lecture and I'm such a dummy dum dum. I can't understand it, but as I'm trying to understand it, I realize, oh, he's a dummy dum dum. He doesn't understand how to explain. He has no idea what he's talking about. It's a terrible explanation. It's basically incorrect. It's so bad. It's such a terrible explanation that if this is how you conduct your experiments in your physics, you should change your job. Wrong job. And I feel like such a dummy dum dum. How am I not understanding these things? Yeah, because you don't know how to explain. And you're so sloppy in your explanations that I don't know who passes your courses. I don't know. You have to be I don't know, super genius. Anyway, the speed of light experiment. That's it. That's a pretty good explanation, but I've seen a better one. They actually showed the original equipment. There's no way I'm going to find it. I drank a second cup of coffee today, but I barely slept. Oh, that's me. That's so funny. And there's two people watching. That's me watching me. Can you believe it? Me watching me. Let's watch me watching me. There it is, me watching me. Let's hear me watching me. That's me watching me. Can you believe it? Me watching me. Let's watch me watching me. The magic of magic. Okay. All right. So, how to measure the speed of light?
Help of an oscilloscope. An oscilloscope can take data at a rate of.
They did not use an oscilloscope. Don't do that. Just do the original experiment. You can do it literally at home with a cardboard. Just use a cardboard to run the experiment. Why are they teaching it with the most sophisticated tools? Teach it with the least sophisticated tools and do it at home. Here's Mr. Genius. I'm Mr. Genius. Yeah, Mr. Genius. Fizeau. What is Fizeau experiment? It's like, I don't know. The speed of light. And that's the end of that? No, there's more. I don't know. Okay, let's go back to the beginning. Oh my God, this is so painful. I don't want to watch this. What about this? Measuring the speed of light throughout history?
An occasional series on some of our most important scientific breakthroughs and discoveries. For the first in this series, I want to look at the speed of
8 kilometer or something, then you'll be able to see, oh, where's the eye of physics? Well, let me kind of draw here. And it's only like, it was like...
At least he's teaching it with the most primitive equipment, but of course he's teaching a simulation. He's not running the test himself at home. Yeah, I know. Why no one has measured the speed of light? Yeah, Mr. Genius. Michelson-Morley experiment. What about just the speed of light? Is that too much to ask for? Of course, this one never shows any experiment. Any hope? Any hope? Anyone? Where did I see this experiment? You notice how important experiments are to me and how unimportant experiments are to them? Come on, I saw this the other day. Let's just look at the original. The speed of light experiment original. This one? Fizeau measures the speed of light? Oh, Did he?
Whether the light beam got through the edge of the wheel depended on the wheel's.
Oh, David Butler.
Galileo reasoned
Yeah.
he will. They climbed to the tops of hills to uncover his. In reaction, Galileo reasoned that the time interval through the edge of was in front of the light beam. Time, his eye, traveled to the mirror, block its return, until eventually super slow motion.
Right.
By the time
I hate it when they show simulations. Show me the original equipment. Show me the test. Show me the original test. Oh my God, I'd rather kill myself than falling asleep. Oh my God, what is this? This is another simulation. Oh my God, kill me, please, kill me. Where is it? We already saw this. He's not going to show the original equipment, is he? Oh my God, oh my God, Fizzo.
Speed, and they'd actually estimated that speed by precisely timing astronomical events like the per second. Everything we need to really bright. The camera can see better than me in the dark, zoomed in over a long distance.
I see it.
Do you see it? Step to set this up. Oh, I'm going near the spinner.
He's replicating the original experiment. I didn't even know.
All right, so in the last few seconds, I have decided that I'm going to use the camera as my tachometer recording.
What is that?
Sure, but you can see the cliff out in the distance, and there's a bright green light. That's exactly what's happening because
this thing is rotating
that it
really
takes
fast.
for the light to go to the cliffside and back always remains the same. But in that time, the 2 miles away out in the distance.
Where is it? Something is rotating that he's not showing.
That as soon as we
why not show
machine
the
to measure the
equipment?
speed of light is true to the I watch when the runner crosses back. This disc is moved. So instead of passing through a slot in the disc, passing through the aperture and going into the camera.
It's not showing it. Forget it. We need to see. Let's hear me watching me. Oh my God. Oh my God.
Okay, the first part of this.
Where is? I just want the.
Wait a second.
What am
I promised
missing?
you. This video was sponsored by KiwiCo.
Where is the original experiment? Who conducted the original experiment?
At the speed of light. How we first measured it, for purposes. Through the telescope. Light that Fizzo had calculated.
So was
measured the
Fizzo?
speed of light. Travel wasn't instantaneous.
So I need to see the original equipment. Original equipment.
To measure the speed of light is true to the original.
This video was sponsored.
This is a rough demonstration of Galileo's experiment. Hilltop's approximate flash of light.
Okay, this is Fizzo's experiment to test.
Fizzo.
Does it make?
Sorry, everyone. I did not expect not to be able to find something that I saw the other day. I think we saw it.
How did it is just IO was always absolute. It would never.
I don't know. Michelson Morley. This is too much. Measuring the speed of light.
We will measure the speed of light using a laser and a rotating mirror. The laser sends the beam down to this flat mirror, which reflects the light down to this rotating mirror, traveling a distance of about 4 meters.
You can use this key to align the mirror to send the beam down a long hallway to a mirror positioned about 40 meters
we
away.
don't need that.
Found that his values for the deflection of the
Okay, I don't know. Speed of light experiment by Michelson. Michelson also had an experiment. Oh, interesting. It's a different experiment than Fizzo. Wow, interesting.
It can be loud, and so this helps. Yeah, but my
Oh my god! Wait, are they wearing masks?
yeah.
3 years.
Also, my secret is
God, COVID.
I rarely use these
The COVID
because I find that although they're a good,
yeah, he's overweight. He has a belly.
yeah,
That's
also,
really dangerous.
Also, my secret is I rarely
Wearing a
use
mask
because I find that although they're a good sort of starting place.
So dumb.
Okay.
Okay. Okay. I'm about. Let's hear me. I'm about.
From what I can
I'm about to give up. Okay, we have comments. Works. The sound. What do you mean the sound? I don't know what you mean. Oh, I think you came in late.
observing the state of Israel.
Yeah, by the way, generally...
I don't know.
The speed of light is defined as 299,758.
Defined? What are you talking
Working at the
defined?
Take Romer's
The speed of light is defined.
calculate
A kilometer or something per second.
Interaction.
This is one of the best.
As long as there is the same number of
the world. I hate news unless it's ground news. The photon.
Somebody has something to say. Oh my God. Senus, you can join me. In VC. And what is this? I don't know. We're alive. He doesn't know we're alive. Oh my God. All right, 2 minutes. Okay. I don't know why I can't find this simple experiment. I saw this, I think, yesterday.
In times of antiquity, light was a really mysterious thing. There are about 8 in my basement. If I put my hand feet, and if you wonder why I'm using 1,000, did better than that.
I don't know.
Also changes, and as Earth is orbiting, see here.
Original equipment. The speed of light experiment. Original equipment. What am I missing?
In our last lesson, we talked about a couple of things. We talked about what the principle of relativity means. In general, relativity isn't a new thing. The first get results, but now we have fast doesn't experience any net motion. Ether, or just ether for short. Ether was first proposed in ancient Greek times as a substance found above the earth, what was called the terrestrial sphere, back when such names as Plato, Aristotle, and Ptolemy were leading intellectual luminaries. In the 17th, 18th, and 19th century, ether was thought by some to be a substance that permeated the entire universe. It was
Sorry.
There was a proposed answer that originated in the 1600s when the question of the wave or particle nature of light was raging. Those who held to the wave theory of light proposed that the substance that transmitted light was called the luminiferous ether, or just ether for short. Ether was first proposed in ancient Greek times as a substance found above the earth, what was called the terrestrial sphere, back when such names as Plato, Aristotle, and Ptolemy were leading intellectual luminaries.
Wait, he has a mustache, so he's ex-Air Force? Oh, hello. What's up? Can you hear me? Oh, you're muted. You gotta unmute yourself. Let me know when you
What's up?
Yo, what's up? How are you?
Lower the volume of the stream. Okay. So now now it's fine. Are you listening to me?
Yes.
Okay, nice. So, it's interesting. I saw you for the first time in like PWF. Yeah, like your debate. And then I subscribed to your channel eventually.
Wait, speak slower. PW, playing with fire. PWF. Okay, yeah,
Yes.
That was my debut on YouTube. Yeah. So you saw me on playing with fire?
Yes, and then I subscribed to your channel, and now I got some interesting stuff. Yeah, you're looking into the same type of stuff as I am.
Okay.
Basically.
Yeah. So, well, like, what did you figure out thus far? What do you think about what do you think
It's not very different from what you figured out, really. It's there has to be a medium, otherwise like things just don't make any sense. Like for example, you have two magnets. How does one magnet know where the other is?
Yeah. But what do you think?
You'd have to either model it as
Yeah. What do you
the
think?
magnets emitting
Right.
magnetism all the time.
But what do you think
Yeah,
about
okay.
my proof today? I was able to prove that the speed of light is a constant for all moving observers. Did you see that proof?
I don't think I saw that until the end. I think I just saw your discussion a bit with.
So it's actually very
with
simple.
another-
So it's actually very simple. So you take a rubber ducky, right? So I came up with this rubber ducky thought experiment. So the rubber ducky internally has a clock that works on the very waves. It works on the water waves. So it does tick tock through the water waves, just like the dialect sound clock. Are you following thus far?
Yes, yes.
So it tick tocks, right? So the rubber ducky is actually calibrated when you buy it at the store. So it's calibrated to tick tock, let's say at 1 meter. Let's say it's 1 centimeter, and it takes 1 second, or let's say 100th of a second, right? Because centimeter is 100th of a meter. So let's say it takes 100th of a second for it to tick tock internally. So that's how it was calibrated. Now, it doesn't matter what the speed that it's moving at, it's always going to tick tock. It's always going to tick tock that distance. It's always going to tick tock that distance. So it's always going to be tick tock over the same distance. So it's always going to be measured as a constant if the time that it's measuring is the tick tock. So it's the distance is always going to be the same. It doesn't matter if the duck doesn't know if it's moving or not moving. All the duck can measure is the tick tocking, but the tick tocking, that is the clock. It always takes one tick tock.
For the duck, yes, it always takes the same time. It can't distinguish.
No, but don't say time. Don't say time. It always takes the same tick tock. There is no time because, I mean, time is
there really is no time. It's just a measure that we
exactly. Time.
I mean, if there is time, like as in like you could like time travel or you could do stuff like that, but we don't have access to that. We can't.
I don't know what time is.
Measure it.
Like, I don't know what time is. All I know is how to measure time. Like, scientifically, I don't know what anything is. I just know how to measure the thing. That's science. In science, we don't know what the thing is. We just know how to measure it. We can talk about its properties. We don't know what the thing is. We just know what the properties are. We know how to measure it. We know how to measure it. So time, I only care for time just as much as I can measure it. Now, the rubber ducky is a clock. It tick tocks. That is how it clocks. It clocks. It just clocks. So in order to calculate the speed of the waves, it literally tick tocks. That is a wave. It waves there and back. That's the quote time, and the distance is always the same. So it's distance over the tick tock. So it's whatever the distance is over the same tick tocking. The distance never changes. The tick tocking never changes. Therefore, the speed can never change. And that's the proof that Einstein postulated. So I don't need to postulate it. If I just assume ether, I get the speed of light as a constant for all moving observers. Do you understand?
I understand, but that's actually a little. I think even that is like doing too much.
No.
For this.
No, otherwise,
It's very
otherwise,
simple. Like
no. How?
like it's just wave mechanics. Like if your medium isn't
Yes.
changing, the speed in your medium doesn't change. That I mean, it's really that simple.
No, but you have no.
It's
But
almost simple because like if you're going to try to argue this, people will just say it's too simple.
what?
It really is that simple. If you're going to try to argue this, you'll be accused of being too simple immediately, right? Like if you're not going to do it like that lecture that you were watching, it's just too simple. Scientists should have figured that out, but the reality
I
isn't.
don't.
It is that simple.
I wouldn't say that. I would just say, because I was thinking about this. How can I prove that the speed that the rubber ducky, the speed of the waves that the rubber ducky measures, whether it's moving or not, how can I prove that it's always a constant speed? I didn't.
It has to be. Yes, that's true. It has to be the same always.
No, we don't know that. Einstein postulated it, but I need to prove it that it's true for all. I need to prove it for any rubber ducky moving at any speed. So I proved it.
Yes, you can. Yes, you can never, because the relationship between the time that it takes and the length.
Don't say
that
time.
you get.
Just don't. As long as you don't say time, everything is fine. When you say time, everything falls apart. That's the confusion. There is no time. There's only measurement. There's only the clocking. It's because
yes, the clocking at the distance that
exactly, and the
goes to the medium.
And
the relationship is always the same.
Of course, it's by definition. You could say it's by definition always the same because it's the same distance and it's the same clocking. It's just the definition of a clock. It's a definition of the tick-tock. Yeah. So by definition, it's so strong. This postulate is so unnecessary. If you just assume a medium, you get the speed of light is a constant by definition for all moving observers.
Yeah, you definitely do. That's a good thought experiment. You definitely do that. You definitely do get that.
I definitely get it.
Yeah, yes, it works like that, like you're saying.
Yeah,
it has to work. There's no other way it would work.
Right. I was thinking, like yesterday, I came up with this experiment, and I said, I need. I mean, not experiment, but I said I need to be able to prove. If I can prove Einstein's postulate, then basically I can do to Einstein what Einstein did to Newton. So Einstein said Newton was correct from a certain point of view. Now I'm going to say Einstein is correct from a certain point of view. So
easy,
right? So
I think it's just all triangles and wave mechanics. I don't. The thing is, I don't see any need to interpret this any further. That's like why do we need a theory of relativity that says that objects? I mean, it's just if you look at the gamma in the Lorentz transforms, like first of all, Lorentz, you know that he made those transforms. Those would be like measurement corrections to something measured in the ether.
Yeah, like I don't know.
He disagreed with Einstein. He believed in the ether and disagreed with Einstein. So the formulas were already made to be wave mechanics in the ether. So it's all the same. Like the mathematics doesn't change at all. So what changes from Einstein is like the interpretation. That is just a very strange interpretation.
It's not even the interpretation. It's the weird thing that Einstein's theory is not scientific. It's like everybody before Einstein was thinking. What?
It's philosophical. It's not mechanical.
I don't know what philosophical. It's either it's scientific or it's unscientific. Einstein's theory is not scientific. It's not mechanical. Einstein's theory of
that's what I'm saying.
So if I came up with a new definition of science. Science must be mechanical. If science is not mechanical, it's not science. So all the nonsense with modern physics that it's not mechanical. You can't.
Physics has to be mechanical, but like if you're thinking about like psychology or social sciences, that's a little bit different. That's more dynamical. That's more relationships between people and stuff like that. That's different.
No,
but physics has to be mechanical. chemistry, biology, that has to be mechanical.
No, what do you mean? But why is psychology not mechanical? Why would you say psychology is not mechanical?
Well, how would you make psychology mechanical?
What do you mean? The brain is a mechanical. It's a mechanical.
But that's neurology. That's not psychology. Psychology is about like studying, people's personalities and traumas
you
and
can
stuff like that.
right, but these are you can derive them from mechanics. There's no magic. It's not like
I mean, I guess you could derive them from mechanics, but it's like you could also study them without that.
Right, but it's not. There's no magic in psychology. That's the point, right? The point is that you can psychoanalyze a person and say, well, this happened to the person when they were a child, and this caused them a mental scar, which is right? A mental scar. That's a mechanical thought. There's no magic. It's not like quantum wave duality and probability wave something. I cannot imagine those words. But a scar, like a psychological scar, that's a mechanical idea that there is a scar in the brain, and the brain is just a bunch of connections, and each connection represents.
In a way, you're right. It's just going to be a lot more fuzzy. There's going to be like a lot of stuff.
No, but I'm a brain scientist. That's my day job. So for me, the brain is it's completely mechanical. I don't have any issues. Of course, everything is mechanical.
Yeah, but neurology, yes, it is. But psychology, sociology is even like over psychology.
Neurology is actually the medical field of the brain. That's like how to like doing surgery. That's not actually. I don't care so much about that. I care about neuroscience. So the neuroscience is a very mechanical. Like if you ask me to build, if you ask me to build a human robot, I would tell you, let's take the human, and copy paste, because every part of the brain, that's where you should put the AI chips that are relevant. Like whatever is relevant for speech, put it in area, I think 48. It's right next to the left ear. Anything that has to do with hearing, put it next to the ears, right? The left and right. Anything that the brain is separated in such a like the perfect design of a robot, of a humanoid robot, is the human body. It's amazing. The more you study the human body and the human brain, and you want to build a human robot, you're like, copy paste. The human is already the best blueprint. Just copy paste. It's so perfect. And the same goes. What?
A little bit different with AI. It's a little bit different with AI. Like,
no, it's.
By the way, my formation in university is AI.
Right, but I'm a theoretical. A little bit different. I do brain research. I do brain research and theoretical AI. So I can tell you what things nobody knows. So anyway, enough of that. Anyway, so going back to the definition of science as mechanical. So Einstein is not science. Einstein is not a scientist by my definition. Anyway.
Yeah, I agree with that. It's like it's just kind of even in other things like quantum mechanics and stuff. It's just a lot of interpreting things that, in the end of the day, it's not actually that hard to explain them without really not really much theory behind it. Because like these wave mechanics, they're just mechanics and it's just geometry and.
Right.
I have searched for this issue because like I got some physics at university and I learned this and I was actually pretty good at this, but it always like kind of rubbed me the wrong way. It just doesn't make much sense.
Right.
And some of this I have not seen anything that can't be resolved. Just like it's just not necessary to make all these affirmations that the speed of light and assumptions, like they're very easy to to understand from a mechanical point of view. If you just understand how waves work and how triangles work, it's not that hard. And even knowing that that most of these things were actually developed, most of the mathematics was actually developed for the ether. Like they just got really confused with the Michelson-Morley experiment. That's basically what happened. But the mathematics really doesn't change that much from one thing to the other. So there's not that problem. By the way, have you ever seen like Newton's bucket experiment?
Yeah, I've heard.
Are you there?
I heard a lot about it. Do you have any issues with it? Have you not resolved it?
Yeah, I do, because think about it. I think Dialect had a video on that. Supposedly, like Newton wanted to prove that you couldn't do everything with relative frames. There was a discussion back in the day.
Wait, what do you?
You need whether.
Wait, but what do you think? Did you resolve the bucket experiment or not?
Did I resolve the what?
The bucket experiment, the bucket thought experiment.
Yes.
So what's your?
I'll tell you. I'll describe the experiment first.
Mm-hmm.
The experiment is like you have a bucket with water,
Mm-hmm.
right? And the bucket is at rest.
Mm-hmm.
And you are at rest with the bucket, and then the bucket starts spinning, and you start spinning with the bucket.
Mm-hmm.
And at some point, you have to accelerate the bucket, but then all the velocities and stuff like that are the same. But what happens is that the water will go up the sides of the bucket. You get like a concave thing in the water.
Yeah.
You understand?
Yeah, I think it's a parabola.
Yeah, exactly. So Newton argued that because of this, we needed absolute motion, because the relative motion of everything in this experiment is the same in both cases, and yet both cases are different.
Mm-hmm.
And it actually can be seen that both cases are can be measured, and all of that both cases are different. So then someone who was basically kind of like Einstein's mentor was Mach.
Yeah,
that's his name, Mach. He said that this wasn't like correct, because this only happened because of the gravitational field, and if it wasn't for the gravitational field, the water would be constantly, it would just go up the bucket, and it would leave the bucket.
Mm-hmm.
But I mean, it's very easy to resolve this. Like, all you need to do is let's just say the bottom of the bucket is the source of the gravitational field, and then you solve the problem. So because whatever the source of the gravitational field is moving with the rest of the frames. So you don't have relative motion again. And the other one is probably the most silly one is you plug the bucket, and you really don't get in. Eventually, everything will be at rest as well.
You do what?
So I don't know how this survived until you plug the bucket.
Plug it?
Yeah, so the water doesn't move. At some point, it will be at rest with the bucket.
What do you mean plug? Plug the bucket? What is plug? Put
a lid on it.
And then what happens?
Yeah, and eventually everything. Then eventually, if you stop accelerating, eventually all the things in all the components of the referential, whatever they are, they can all be moving with the same speed. But
I'm not sure.
You will be able to distinguish.
Mm-hmm.
Yes, the idea is that you can never relativize acceleration, because if you accelerate something and then it moves at a certain speed, it will have impact. If you're accelerating something, or if there's a force or something like that can't be made relative. Like, that's kind of Newton's idea. Like, Newton didn't agree with relativity because forces can't be made relative. It's not like something exerting a force on you and making you accelerate in a certain direction is equivalent to you seeing something else being exerted a force on and accelerating in the opposite direction. That's
Anyway,
what we're saying.
I'm not sure about your resolution. I'll tell you my resolution. So here is the bucket. The question is, how does the bucket know to curve when it's spinning? How does the bucket know that it's spinning if let's assume an empty universe? So Mach would say in an empty universe you can never spin a bucket. There's no definition of spinning.
Yeah, basically.
Right. So I think that's nonsense. So I think the resolution. So I think the resolution is to think.
Yeah, even that is already nonsense, but because the bucket would become more tense, so you would be able to measure it.
What do you mean? But the question is, what would happen?
There would be tension because there's a force.
No, but the question is, how does the bucket know to behave the way it behaves? Anyway, my resolution is as follows. You can watch if you watch my stream, you can see what I'm showing, or you can.
Oh yeah,
yeah, you can. It's a Newton's bucket. Anyway, the solution, the thought experiment is to think about. Here is your friend. Let's say he's your friend. He's in a spacesuit, and you are here in a spacesuit. You're both in spacesuit.
Are you going to do the rocket one?
No, it's an empty universe. Empty universe.
Okay.
Now, you're moving in this direction, and your friend is moving in this direction. And as your friend, right, you can tell. Well, you can assume that your velocity is 0. Your friend can assume his velocity is 0. It doesn't matter because both of you realize that there is a relative motion. Let's say he sees you moving in this direction at I don't want to make some crazy speed. Let's say 10 miles. He measures 10 meters per second that way, and you measure him moving towards this direction at 10 meters per second. Okay, 10 meters per second. All right.
Repeat that. I got a bit lost with that.
Okay, so you're in this empty universe. Empty universe, nothing. Just you and your friend. This is you and this is your friend. Both in spacesuits. You're moving at 10 miles an hour relative to your friend, and he's moving at 10 miles an hour relative to you. That's natural. It doesn't matter if actually you're stationary. It doesn't mean anything because the empty... we don't have an interferometer to measure who's actually moving relative to the ether. So we're just assuming, right? You can assume that you're not moving. He can assume he's not moving. But at the end of the day, he sees you moving this way, and you see him moving this way at 10 miles an hour. Okay? Now, as you pass by each other, you hold out your hand, and he holds out his hand. So you grab hold of each other. Now, you both agree that you're going to start rotating. As soon as you hold on to each other, so here is him, and here is you, and as soon as you grab each other, you both agree that you're going to start rotating because you had a tangential motion in that way, and he had a tangential motion that way. So now you're going to be spinning around this center of mass, and if at any point you let go, you will each go again in a tangential direction. So spinning is, you don't need the universe for spinning. You just need relative motion in order to accomplish omega. In order to accomplish right, you had inertia, you had linear inertia, and here you have rotation.
Yeah, but during the spinning, they don't have relative motion to each other. That's
of course they do. Nothing changed. Of course they do.
No, they don't.
What do you mean? Of course they do. At any second during the spinning, you're still going in that direction, and he's going in that direction. At any instant spinning, you're still going in a tangential direction just like in the beginning. At any instant, you're still moving tangentially towards this relative to the circle. So nothing ever changed. And that's the simple resolution to the definition of spinning in an empty universe. It comes if you believe in inertia, if you believe in linear inertia, then you believe in angular inertia. I think I is rotational inertia. I think I is equal to, or I is the moment. I don't remember the letters, the Greek letters. Omega is like the angular velocity. I is the angular inertia, and together it's equal to who knows what. I don't know. Anyway, but this is just a derivative of linear inertia. If you believe that linear inertia doesn't depend on the rest of the universe, then there's no difference between linear inertia and centripetal and rotation about the bucket. You and him are basically the bucket. Here you are rotating, and that's it. And Newton's bucket is resolved. I never understood the problem. What do you think?
Okay, wait. The last part. The last part.
So you were moving. I'll start again. I'll draw it from the beginning. So let's create a new Newton bucket 2. Newton bucket 2.
Okay, but I understood until the part where you just need to. The thing is, how does this solve Newton's bucket?
I'll just.
That's my doubt.
Okay, here's person A.
I understood. You don't need to explain again the.
No, it's just gonna be faster. And here's either person A or A and B.
Okay.
They're moving past each other, but as they pass each other, they grab each other. As they pass each other, they grab each other, and still they're maintaining the linear inertia. But now because they're attached, it becomes angular inertia. It just becomes angular, but it's still linear. Nothing changed. The inertia didn't go anywhere. It's right. If they let go, they're gonna continue going either that way or whichever way, depending on the point. Let's say after 10 exact rotations, they let go. They're gonna continue about the original direction. So
okay, but Newton's bucket, the bucket, then the bucket is like the referential. So
the bucket is the case where you're attached. You imagine you two drop, right? This tension is causing the parabola in the bucket. That's the tension. This is you and this is your friend.
About the
what? What's the question? Why you get the parabola? I mean, the parabola is because obviously you need either you need to accelerate that way, or you have a force of gravity. I mean, the question is, why do you get
No, the thing is the Newton's bucket is a bit different from this.
No, the Newton's bucket, the way I understood it, the dilemma is, do you need the universe in order for the bucket?
Yeah,
so I don't need the universe.
No, it's yeah, that's one part of it. But no, you don't need the universe. But in the case of Newton's bucket, like at some point, everything is at rest again.
Why?
Like,
what do you mean?
Supposedly, quote unquote rest. It's not really at rest.
No, that's a violation.
What they argued.
No. Nothing is at rest ever. No, nothing goes to rest because the initial inertia is maintained. Inertia is, according to Newton, inertia is conserved. This is conservation of inertia, conservation of momentum. This is the law of conservation of momentum. It cannot go away.
Yeah.
Anyway, I don't think it's worthwhile to talk about Newton's bucket. I'd rather talk about quantum mechanics. Have you resolved any quantum mechanical paradoxes?
Yeah, there's something about quantum mechanics that Now I'm trying to remember the name of the experiment. Let me just try to ask ChatGPT.
Okay.
Because have you ever seen that experiment where they supposedly got that the electrons cannot have like continuous spin?
Yeah.
Have you
Sure.
ever seen that?
That's exactly. I was thinking.
What's the name of that experiment?
Gerlacht. The something girl.
Yeah, something like that. Stenbar girl or whatever.
Gerlach. Yeah, something weird. A weird
Yeah,
name.
something very strange. Wait a minute. Let me ask this.
I'll look up.
Experiment that prove electron spin
Yeah.
inside.
Electron spin experiment.
Yeah. Stern Gerlach. Yes.
Yeah, Stern Gerlach.
So you know that experiment, right?
Yes. So
what's your view on that experiment?
I didn't look into it. I mean,
No.
we can think about it
Why didn't you look
together.
into it?
So the electron is a wave.
Okay, you want to see a video that explains it?
The problem is I cannot. So yeah, I'll let me show. Yeah, let me show an experiment.
I can see on YouTube. It's okay.
Okay, so I'll share it. So no one is hearing you now. I'll play the video.
Particles passing through.
1 second.
The physical explanation turned out to be electron spin.
Wait, what?
The physical explanation turned out to be electron spin.
Okay, so he's
Electron.
What?
I'll give you a link with one.
Usually I go through one by one, and then I listen to a bunch of them, and then I pick the best one.
Yeah, that takes a long time.
So you have a good one?
I'll just give you one. I think this one is probably fine. It's just all we need is the setup. So the setup is already on the thumbnail.
Okay,
so
let me see.
Hi everyone.
enough.
This video is about the Stern-Gerlach experiment. In this experiment, silver is heated so much in a furnace that it becomes gaseous. A few individual silver atoms
So
leave the
basically,
furnace through
the green
I
and
do what he just said. Something about a furnace? Is there a furnace in this experiment? Silver. Anyway, okay. Let me replay the beginning.
the Stern-Gerlach experiment. In this experiment, silver is heated so much in a furnace that it becomes gaseous. A few individuals.
I think he's difficult to understand. I think he said that something happens and the silver becomes gaseous. Okay.
Silver atoms leave the furnace through a.
So the silver atoms leave the furnace. Let me maybe CC so we can see what he says, and I'll maximize it. Okay.
Small aperture in the direction of an inhomogeneous.
The silver atoms leave it to create an electron beam. By the way, I'm listening on YouTube, so there's a delay.
Okay, you can watch it on my stream if you want. So so there's an aperture. Okay, there's an aperture.
Magnetic field.
There's two magnets, inhomogeneous magnetic field. Okay.
Behind the magnetic field, there's a photoplate, which the silver atoms hit and leave an imprint.
That's good.
The result is that the silver atoms are deflected either up or down.
Yeah, it's really weird. So it's either they're up or down. Now, the way I see quantum mechanics is everything is a wave when it's moving, and when it's
but but like my problem with this is that you haven't got that in the video. Is that the prediction that they made was supposedly that there would be it would be like a parabola, there would be some in the middle.
Okay.
Right.
I don't know. I mean, well, let me think about my prediction.
What would be your prediction?
Right.
Here?
So let me
What would
think.
be your prediction here?
Right. So my prediction is that everything is a wave. All these particles, all the subatomic particles are waves, as long as no one is interacting with them. When you interact, when anything interacts with anything, then it becomes a particle. And then Schrodinger's, I think, equation takes hold, and Heisenberg takes hold, and then it materializes with a certain probability, and and so, stuff like that. But until then,
I don't. I have some problem with that because like things can't be waves. I think most things they wave. When they start at high speed, they end up waving because they probably there's some kind of medium and they go against that medium and they create waves in that medium. It's like if if you do you like shoot a bullet, you create waves in the air, right? Something like that.
No, I don't want
Create
to
a very loud sound.
Look. So when
So if you shoot an electron, you create waves, and eventually it's probable that the electrons just ride the wave, whatever an electron is. So you don't even know that.
So I started, basically I came to ether from gravity. So I started from black holes. I started 2 weeks ago from black holes, from veritasium's last video. Something weird happened when you follow Einstein's math. So I did a video after video after video, and I kept analyzing his video. And as I was studying his video, I was also thinking about what's going on with the black hole. What is a black hole? And I don't remember exactly what happened, but at one point I went back to Newton's gravity, and I did F equals ma, and F equals gmm over r squared. So ma equals gmm over r squared. So the two m's drop, and actually, Lenny Susskind does this in his course, Introduction to General Relativity, in lecture 2, or right in the beginning, or maybe even lecture 1 or 2. So he says ma equals gmm over r squared. The m's drop because you divide by m, as long as it's. He didn't say, but I think you need to assume m is not 0. So a equals gm over r squared, but a is a vector because r is a vector. So you have a Newtonian gravitational acceleration field equation, which describes the acceleration of test particles in the universe, assuming a point mass at the center of the universe. Basically, very similar to Schwarzschild.
Yeah, that's kind of similar to like Machian gravity, similar to that.
Whatever. I mean,
kind of does.
It's just Newtonian gravity, but the point is that's the field of acceleration. Meaning, if you put a test particle anywhere in the universe, it would start accelerating according to the Newtonian acceleration field equation, vector field equation. Now you can convert the acceleration field equation of a equals gm over r squared, and you can convert it into velocity if you just integrate it. So you can say the velocity is equal to, and I don't remember, I think it's 2gm over r, which already reminds you of Schwarzschild. That's very close to Schwarzschild solution. Anyway, but that gives you a velocity field equation. Velocity field equation means every particle in the universe is moving at that speed, where at infinity the particles are moving at 0, and very close to at r equals 0.
Yeah, very close to
infinite
of gravity.
Yeah, it speeds up.
Yeah.
And but this explains a black hole, so you can derive Schwarzschild from that. But you can also see that space is flowing. And Lenny Susskind says this. Right. So Lenny Susskind says this in his lecture, that you can imagine, and he explains this with with Gaussian flow and Gauss's theorem and divergence. He teaches divergence. So, But he says it's a good analogy to think of gravity as a liquid. Okay, but when but when I was analyzing it, I was saying it is a liquid. Otherwise, what's dragging the apple towards the earth? What's dragging the moon towards the earth? It has to be a liquid.
Yeah, the only problem I have with that is like, where is the liquid going? Right, like.
Yeah. So
the liquid is kind of draining in the air, but where is it going?
It's draining into massive particles for some reason.
Yeah, it seems like that. Like, that's actually, I sent you that guy distinctive. That's actually his theory.
Whose theory?
Things absorb distinctive. The guy was the ethereal mechanics.
Yeah, that seems to be the case. I mean, and
yeah, that's what it means. Like, it says that things need to absorb energy to continue existing, and that the universe is absorbing.
No.
That mass is absorbed ether. And he explains it with that.
No, I wouldn't say that.
Yeah, that explanation.
I would just say that it seems.
I don't think that's really correct either.
Yeah. All we know.
I think you could model it like that, but it's probably different.
Right. All I know is that space seems to flow into massive particles. Now, massive particles, we know, receive their mass from interacting with the Higgs mechanism.
Yeah, and what I think is that eventually the ether becomes stationary in relation to those massive bodies.
No, I
think that makes perfect sense. Because it's constantly draining into them, it eventually becomes somewhat stationary. You know, like it can't drain anymore, so it just becomes like they're like attached. But I think you think that there is like a constant flow all the time.
Right, and the constant
I don't know if that's necessary.
Well,
because even if you think you can have gravity even without that, like you can have gravity. For example, the way this thing tries to explain gravity, now I don't know if this works very well, is that because there is some separation between charges in atoms, then they tend to be attracted to the ether. So basically, like a nucleus that is positive on an atom will tend to be attracted to the ether, and the outer ring, which is negative, will also tend to be attracted to the ether, because the ether is because the ether would be like less positive. It would be like negative around it.
No, the ether.
Something like that.
No, I don't think so. Look.
It would become negative around it, and so it would be attracted to a zone that would be more dense.
No, that's not how I see it. I see the ether as the fluid of gravity, the fluid that drags me. Right now, I'm being dragged towards the earth by an intense fluid flow. I did the calculation. It's flowing in right now at 10,000 meters per second at Earth's surface, towards the center of the earth. It's flowing through me, and it's dragging me towards the center of the earth. It's dragging the apple.
That's possible. The question is, how do we confirm that?
So I explained that we can, with an interferometer, with a very accurate.
Oh right, the microphotometer.
Yes.
Yeah, that would be good. Yes.
Right, but
there are some people who try to do that, but it's on YouTube, but that's kind of impossible. Like, it's impossible to tell if it has a real effect or if it's just like their apparatus going around. Because there are some experiments like that on YouTube.
Right.
It's just kind of impossible to tell whether they're getting a result or why they're getting the result they're getting. Because they do get a result, by the way.
Yeah, but
the question is that why are they getting that result? Is it because of the apparatus that is under some stress, because of gravity, or is it because something else?
No, it is gravity.
It's not clear.
No, it is.
Yeah, but I'm saying it's because, like, imagine you have like a beam splitter. If when you move the beam splitter vertically, if it changes a little bit, then you will already have a result, just because it falls like a tiny bit, even if it's just very well like attached to the rest of the apparatus.
So
that's the problem. It's like working through the errors. But you've already talked a lot about that.
right. So
Yeah.
so
Start to measure that.
right. So I would say that science, that I've modified again my definition of science. So I would say that you cannot conduct a scientific experiment by, by the very definition, I think Bacon's definition of science is the gold standard. So I don't think you're being
Hypothesis testing. Yeah, I know where you're going. Yeah.
So right. Hey Hamburger. So you need to. Hey, what's up? So you need.
Hello.
So you need to make an accurate prediction of what your experiment is going to actually demonstrate. And you need to be within an error. You need even to tell us what is the error that you're expecting. And this is the scientific method. So just to tell me that I conducted a Michelson-Morley interferometer experiment and I don't know, didn't get a result, that's not science. Science is I know exactly what result I'm going
to get. But they made a prediction. They made the thing is that it's very hard to find exactly what their prediction was, but their assumption was a bit weird. Like their assumption was basically like I never understood their assumption. That's one of the things that it always stinks when I was learning this sort of stuff, because it's not clear why they supposedly, people say they made the prediction that the Earth, as it was rotating, there would be differences in speed of light, because the Earth would be like kind of going through the ether. The ether would be stationary and the Earth would rotate in relation to it.
Exactly.
But then why don't you consider the speed of the Earth around the Sun? Why don't you consider the speed of the Sun around the galaxy? Why do you not consider the speed of the galaxy?
No.
In relation to the ether, it doesn't make sense.
I'll explain. That's exactly what you just said. That's exactly what I say. So first of all, I'll tell you the numbers. So if you build an interferometer, it's if it's gamma.
Oh yeah, I saw that live stream. Yes, I saw that live stream.
Right. So if you build it based on gamma rays, that's already picometer sized wavelength, and that's a very accurate interferometer. And then I made the calculation, then that should be, I think, around 1 meter arm, just like Michelson-Morley's experiment was. Maybe it could even be handheld. It could even be inside your iPhone. But the question is, what are we measuring? So anyway, you can build that. You can build with thousands of mirrors to simulate like kilometers long arms, or you can build it in space, or even on Earth, like in the middle of the salt lakes. So you're gonna anyway. You can build it in any which way. Anyway, so the speed of the ether is the speed of gravity. So it's about 10,000 meters per second going into Earth right now through us, and it's about, I don't know, there's different numbers. The speed of rotation of the Earth is either 1,000 to 1,700 meters per second. From the east to the west, whatever. I think no, it should be. It's rotating using the right hand rule towards the north. So if your thumb points at the North Star, so your fingers curl, and that's the direction of the rotation of the Earth. So we're spinning into the ether flows into the Earth in straight lines because it is gravity. It is Einstein's general relativity. But the Earth is spinning through the ether. So at the equator, depending on, we need to do the calculation of what the expected speed is. I've seen numbers between 1,000 and 1,700 meters per second. At the North Pole, it's 0. So I would say, like, where Michelson was in Ohio, that's basically halfway through. So I would say it should have been, I don't know, 500 meters per second, because he was.
Yeah, but that's the thing. Why not consider that if things go through the ether like that without any drag, why not consider the speed of the galaxy?
Because
that's the part that doesn't make sense.
Because you can predict the ether just based on general relativity. General relativity describes the ether, but instead of saying
the equations are the same.
What?
The equations are the same, basically.
Exactly.
Doesn't change anything.
Exactly. So just the interpretation is wrong. So everyone interprets general relativity as the curvature of space-time. That is obviously unscientific, completely nonsensical. Nothing of this sort. General relativity describes the Gaussian flow of the ether, and the fact of the matter is, right now, an apple, if it drops directly towards the center of the Earth. The speed of the galaxy, the fact that right now there's galaxies causing tidal motion, even the moon is causing a tidal effect on the apple. But I would say that's insignificant. Sure, you can measure with an interferometer, you can measure the moon. You can measure the changes in the flow of ether because of the moon, because of the galaxy. These are tidal forces, and they should create an effect on the flow of the ether, on the flow of the fabric of general relativity. So yes, or if you want to say curvature, Einstein said his nonsense curvature. Everybody repeats after Einstein the nonsense of curvature of space-time. Sure, that's predictable. And maybe even
Tesla was very. One thing, just a curiosity. Tesla wrote a poem about Einstein when he came up with that theory, calling him a fuzzy-haired crackpot.
I read some of Tesla's.
Yeah, he wrote a poem dissing him. Wrote a diss track on Einstein.
I don't appreciate Tesla. I don't think Tesla was as bright as people.
You don't? Oh, I like Tesla. Tesla is like the father of electrical engineering.
I don't know. I don't have an opinion so much. But anyway, so let's get back to the Stern-Gerlach. Hamburger, by the way.
Yeah, let's get back to that.
Just 1 second. Hamburger, we're doing really super advanced physics discussions. I don't know if you're going to be able to follow. It's really.
I can look up the things I don't understand. So.
You're able to understand some of the things?
Yeah, and I can look them up when I don't.
Fantastic. Okay. Anyway, so let's talk about the Stern-Gerlach experiment.
Yeah, what's your prediction? What like you understand the setup or not?
Yes. So I didn't give it any.
So you shoot a beam of electrons, and there are two magnets, and the magnets deflect the beam.
Yes.
Right.
Yes.
So what would be your prediction here?
Right. So from my understanding of general relativity and a simple, thought experiment about what is gravity. So gravity is a very rigid fluid that is flowing very fast right now into the Earth and is not allowing any particles to move. Particles cannot move in this fluid. It's too dense. And anyway, my intuition is particles cannot move in this fluid. So the night I went to sleep, that night I came to this realization. I went to sleep with the thought, how could this be? It's obviously a fluid that is dragging the apple towards the center of the Earth. But how can we live in this fast-flowing fluid? How can we live in this rigid fluid? And how can particles move in this fluid? It just didn't make any sense. It's too rigid. It's almost a solid. because the speed of light is 300 meters per second, 300 million meters per second. It has to be so stiff, so dense that particles. My intuition is particles cannot move in this fluid. So I woke up the next day and I spoke to a friend, and during the conversation, I was like, the only way anything can move in this fluid is if it's a wave. And then I said to myself, wait a minute, but that resolves quantum mechanics with the particle wave duality and quantum field theory. Everything is a wave. That's why we're getting Schrodinger's wave equation to describe electrons through the double slit experiment.
It's not like everything is a wave. It's like everything has to wave to some extent to move.
Everything has to wave in order to move.
Yeah, but it's going against something, so everything has to pressure against something else to move and cause waves.
Right. So everything is, I would say like this. Everything is a wave until it interacts with something. What they call, what the normie physicists, what they call until we measure it, which is nonsense. It has nothing to do with measuring. It has to do with interacting. When you interact with it,
it's interacting with the magnetic field.
I wouldn't say.
But even that, like that's one thing that is somewhat strange, because it's not like you measure particles.
No.
What happens when you put but like in the normal wave particle duality experiment, what really happens is that you get, instead of getting an interference pattern, you start getting a blur pattern, right? You know that or not?
In what case? If you
you know that experiment where you get like the double slit experiment, where you get the interference pattern.
Yeah.
If you put a detector, it's not like you measure particles. You simply you destroy the interference pattern. It becomes a blur. That's what really happens.
So I wouldn't say. Look, I've never
seen. You want to check that experiment?
What?
But in YouTube, it's almost always wrong. Like they say that you don't measure particles. You destroy the interference pattern when you make the beam interact with the magnetic field, basically. It's really what the detection is.
Look, I've never seen the apparatus for the double slit experiment. Never.
But you should see, because it's interesting to see, and you should see like the most representations on YouTube are just wrong. Because they say stuff like you measure particles. You don't measure particles at all. You can't even do that with normal equipment. You have to have super hyper highly specialized equipment that works it works statistically even. You can't even measure them directly. You just measure differences in noise, and you have to amplify that noise. It's complicated stuff. But in the normal double slit experiment with the detector, you basically just destroy the interference pattern. That's what happens. Not like you get a blur instead of the fringes.
Okay, so
when you perform a detection, so it's still an interpretation over what we can see experimentally, which is the kind of stuff I don't like very much.
Anyway,
but yeah.
So
this all wave particle duality, it's very interpreted. Like it's not very clear what that is. Well, what we can tell is that if there is an interaction with a magnetic field or something like that, things change to a point where you no longer have the same behavior that causes the interference pattern. You could even say if you want to do this with only wave mechanics, it's possible to do that, because if you, for example, make a transverse wave interact with a longitudinal wave and you try to interfere them, it gets weird. You don't really measure the proper interference pattern. Then again, you can do this with waves being going in different angles and polarizations. it's a lot of stuff that you can do to destroying the difference pattern. So I'm not like 100% convinced of what I'm actually seeing. I would say is a wave particle duality or something like that. We have an experiment, and the experiment gives the result, and I don't think anyone really knows why the result is that result. Yes, we try to interpret it, but it's complicated.
So I would have predicted this experiment. This experiment follows my intuition one to one.
You'd have predicted those two things.
I would have predicted.
So
I would
like the idea is if you predict the only basically that the things the electrons would be concentrated up and down, or they would be spread all over the place.
No, I'm talking about
That's the idea. That was like what they were trying to test. If they would be like all up, and like half of them up, half of them down, or they would be spread all over the place.
No. I'm talking about the double slit experiment. I never thought about this term.
Oh, okay.
So the double slit experiment, I've never seen the apparatus. I've only seen endless animations. Animations from here until tomorrow and back. But never have I seen.
You can find like the real experiment.
No, you can't.
In YouTube.
Nope.
You can't find it.
Nope, you cannot. I've looked.
No?
There's not.
Oh, there's a channel that's the Action Log that has that. I think he actually does the let me look for it.
Huygens, he did it with a laser. I'm talking about the electron. I don't care about the laser. I care about the electron. Show me. I want to see the electron.
I think he has that with the electron or not. Let me share what he has.
Anyway, so I've never seen the apparatus. I've never seen an apparatus. I've only seen animations. Not a single apparatus. But I did see the results, and they claimed in the video that these are actual results, but of course they did not show the apparatus.
Okay, I think this video that shows like pretty good apparatus.
No, you see it's a laser. You already see that it's a laser. No, it's a laser.
Oh, this one is a laser, yes.
I don't care. I don't care about a laser. I want to see the electron.
But the results are the same. So okay.
I don't care. I want to see the electron because I want to see one by one. I want to see exactly one by one. Because the laser, I know it's a wave. The electron, I know is a particle. So I would be much more surprised to see an electron being dispersed like a wave than a light beam. A light beam is obviously a wave, but an electron is obviously not a wave. An electron you can fire one at a time. A light beam, it's impossible to fire a photon at a time. I don't know what that even means. Anyway.
Oh, you supposedly can do that. Fire one photon at a time. You can do that.
So
Huygens, and he does that on that video.
Yeah, he tried. He couldn't get it. I watched his videos. He tried and tried. It's meaningless. I wouldn't. That's why I don't care for his experiments because he's using lasers. I don't care. I want to see it with an electron. Anyway, so the double slit experiment is very straightforward. It comes directly out of ether. So everything in the ether must be a wave when it doesn't interact with anything. So the double slit experiment, every time you fire an electron, you're actually firing a wave. And of course it goes through as a wave through both slits, interact with itself because it becomes two waves. It goes through both slits, it becomes two waves, they interact with each other. But then when it comes to interacting, with the display, then I agree that there is a collapse, not of a wave function, because that's not a scientific statement, but rather of the wave. So it is a wave, and the wave, when it interacts, it does collapse. So because the energy must be that of an electron.
Yeah, but what does that mean in physically?
Exactly. So the energy of an electron is limited, right? As a wave is a three-dimensional sphere that can grow to the size of the visible universe. So when you fire an electron, it should be able to reach both sides of the universe simultaneously. And it does. As long as if you're not getting its way, it should reach all sides of the universe, of the visible universe at the same time. A single electron as a wave. What is a wave? A wave is a three-dimensional spherical propagation of energy. It should.
I mean, that's a longitudinal wave.
No, it's not. No,
That's a longitudinal wave.
No, I don't think so. I don't think it's a. What do you mean
Yeah,
longitudinal?
transverse wave is a bit different.
What do you mean? What do you mean longitudinal? It's a three-dimensional wave. It's a three-dimensional sphere.
Yeah, that's yes. The longitudinal wave, it works like that.
Fine.
A transverse wave is a little bit different. A transverse wave is like it exists when a medium is separated in two, or in the separation between two media. So
I don't know.
So for example, like an electromagnetic wave, supposed to like is the dielectric and the
No. That's an electromagnetic wave is not an electron. An electromagnetic wave.
No, that's not an electron, but an electron, when you make it a wave, will move like an electromagnetic wave.
That doesn't make any sense.
No, it more or less.
No.
It's hard to describe it. But
no. So we need to.
The idea is that it will. No, electron beam, I think, is transverse. I think electron beams are transverse. Wait.
Electron beam.
Let me check.
It looks like a beam because it's interacting with light, or with smoke, or with a piece of paper. If you can see it, then you've already collapsed the function. Any interaction with a wave collapses it into what looks like a particle. So if you can see it, then that's not the thing. It's not going to behave like a wave.
Okay,
so an electron beam.
So it says here. So this is very unclear. It says here that it's not a transverse wave, but it exhibits wave-like behavior.
Look,
so
when we fire,
kind of strange.
When we fire a single electron through the double slit, I don't know. We can see what it ends up as.
I see.
My intuition is that it feels like a three-dimensional spherical wave. That's my intuition. It goes through both slits. It looks like a three-dimensional wave, because when you fire an electron, you're basically giving it a direction. I don't know. The point is,
I think it needs to move kind of like a wave, because it doesn't have a lot of mass. So when you shoot it like really fast, it causes like compression and distension in the media, and it ends up riding that. It's kind of like if you it's kind of like if you are trying to surf, you and you move and you propel yourself forward, you create kind of a wave on the top of the water.
But there's no water surface. There is.
Yeah, there's no water surface. It's not exactly like that, but it's but just trying to get it in a more or less intuitive way.
Okay, so we're trying to now. Let's start moving to the Stern-Gerlach experiment. So we don't know about the wave of the double slit experiment with the electron going through the double slit. We need to know much more. That
Okay. Wait a minute here.
That's why I need to see the apparatus. I need to conduct tests with the electron. I don't have enough data. They tell me when we put a detector in one of the slits, and they show me an eyeball. What is a detector? Could you show me the detector, please? No. They don't show the equipment.
Yeah, nice if they did that, but but that's not what happens.
So
that's more work.
I need to see the original equipment, and until then.
Okay, yeah, let's go to this experiment because I have to go shopping before stuff starts closing.
So
it's Sunday.
So why don't you go shopping and come back and we'll continue the discussion.
No, let's do this now. Let's do this now.
Okay, so you want
and then
okay, I'll play the video, the action lab.
Yeah, I just want to know like your view on the experimental setup. No, the first one, not that one.
The Gerlach, the first.
No, that's
the Gerlach.
the wrong one.
Okay, I'll show
the other one, the Stern
Gerlach
experiment.
Okay, I'll show it.
Some of you might.
We know. I know what ends up happening, but I don't know enough.
Yeah.
Look.
Yeah, you already know, but like.
Look.
The interpretation of why that happens is what.
No, I need more information about the double slit. I need triple slit. I need more information. I need to buy. I wish I could order online the double slit electron experiment home kit. I want to have it at home.
Yeah, it might exist.
What?
That might exist.
So that's what I need to see. I need more data. This is ridiculous. There's not enough data. I need to study what this electron wave looks like. Where is it going? How does it behave with three slits? One slit this way, the other slit that way, slit that looks like this, slit that looks like that.
If you want to do that, you will need an electron beam thing. And you will need a detector. Detectors are not they can be really simple. It can be some piece of film or something.
The point is, look, I have enough theory to work on. I don't need to run experiments.
Yeah.
So, like I already explained how to build the proper interferometer. I gave many versions of interferometers that will work and will violate Einstein's principles for special and general.
Yeah, I think is if you don't do the experiments, people won't believe you. That's just how it works.
Fine. I'm not going to.
I know that doesn't apply to me because I'm trying to like evaluate whether the theory makes sense, in theory or not.
Look, all I need
is more realistic, what's not realistic. But the majority of people, you will have to do the experiments if you want to.
But the experiment is not going to help us because the experiment is predicted by general relativity. General relativity predicts the ether. It is the ether. So any experiment.
Yeah, we have that problem.
Any experiment we conduct, they're going to say, yeah, that is exactly the prediction of general relativity. You're not discovering anything. So first thing we need to claim is that relativity is unscientific because it's unfalsifiable. They need to tell us, the normie modern physicists need to tell me what experiment will falsify relativity? I cannot keep chasing them. What will falsify relativity? I'm tired of that. They need to.
Yeah, that's correct, but that will never happen.
So,
I mean, yeah, you're right about that. That's the correct way to approach things.
Right.
Yeah.
So it's useless for me to keep. I can come up with more and more and more experiments. They're gonna just say, yeah, it's predicted by GR. Have a great rest of your day. So I'm not. That's why I decided, first of all, that the interferometer is the best thing because
You can see the things that aren't you can do one thing there. You can see things that aren't predicted properly by GR, such as like the shape of galaxies and stuff like that.
the shape of
That
what?
that GR makes shape of galaxies.
The shape of
For
galaxies.
example.
Look. So
Yeah.
what I was thinking.
The geometry of galaxies. It's not predicted properly by general relativity. That's why we have like 90-something% dark matter and dark energy.
So dark
That's the problem, and
so dark energy is very well explained, just like the ether
no,
collapses.
dark energy is just
So just
radioactivity.
so just like ether collapses when it interacts with a massive particles, and that is right, it flows into and crashes into a massive particle. Just like it does that, it also is created out of nothing in the interstellar space, in the intergalactic or intercluster, interglobular space. It seems to be getting created over there because if it weren't getting created and if it would just collapse into massive particles, the universe would very quickly run out of ether and the universe would collapse.
Yes, that's one of the problems of this theory, and that needs to be better investigated and explained.
No. So because ether collapses into massive particles, then we predict that the universe cannot exist. The universe would collapse because of the vacuum created by the destruction of the ether. Therefore, because the universe exists, there must be a dark energy. Dark energy is a direct prediction of the theory of the ether as a liquid. Dark energy is a prediction. I mean, it's difficult to predict. It's unscientific to predict once it's been discovered. But at least it's explainable, not as my biggest blunder, but because otherwise the universe would collapse. The universe.
Yeah, I mean that's a theory. Yeah.
I mean, I think this is exactly. I think this is exactly what Einstein meant by lambda. That he said that he needed to add it in order for the universe not to collapse because it's running out of ether. Because in GR there is ether, and it is crashing. It's flowing into massive particles, but Einstein didn't understand it. He didn't say it. He just said space is bent, curved, space-time is curved, like nonsense like that. But really, space or ether is flowing into massive particles, and the universe is running out of it. It would have run out of it a long time ago because it's flowing in very fast into massive particles. Therefore, you need dark energy. The question is, can we, but what determines the creation? Like, we know how much is being destroyed. I can calculate exactly how much ether by volume is being destroyed from GR. GR predicts exactly how much ether is being destroyed in this universe every second. Given, if you know the mass of the universe, then you know how much basically ether is being destroyed every second. So you need at least that much to be replenished every second as dark energy. So
yeah, correct.
So otherwise, the universe collapses. So I think that is what Einstein added as the lambda term in his dark energy model.
Yeah, I have to check that one. I haven't checked that equation very much.
Look,
But no, no, what you're saying makes sense. It's just that so the ether would be like infinitely stretchable, so to speak, and it would have to compensate itself.
right. You need to replenish because it keeps it keeps crashing into massive particles and it annihilates. It seems to annihilate itself once it is swallowed into a massive particle, but it creates
Yeah, this is like very similar to distinctive.
so you
Like
need
very much on the same
actually
track.
notice that you actually need a positive pressure. So you can view this liquid, but you need to have positive and negative pressure. You need to have high pressure and low pressure in order for this liquid to flow from high pressure to low pressure. So a massive particle is low pressure ether. That's why you have a flow. This is fluid mechanics. So there has to be positive pressure. That means the universe must have positive pressure. It's not enough to just replenish. The universe must have positive pressure of this fluid in order for it to flow into low pressure. So the universe.
Yeah, I'm thinking about the think about the expansion of the universe.
So the expansion is necessary in order for there to be a positive pressure. But everybody talks about these terms, but when they talk about it, they don't talk about the fluid. They talk about pressure, but they don't say it's a fluid. So they're being unmechanical and unscientific. But once you introduce the ether as a liquid, everything becomes so simple and so mechanical. And everything you hear, all these super duper scientists say, no one understands what they say. Suddenly it makes so much sense and it's so simple. It's so mechanical and so simple. I'm not the beauty of the ether. The beauty of the ether.
You can even explain the redshift with that.
Of course.
But
everything.
You can definitely explain that.
The beauty of the ether as a liquid model is that it doesn't contradict any physics. There's no. It's not. I don't have to contradict Einstein's GR or SR or quantum mechanics or any discovery. I'm not contradicting anything. I'm just explaining it better in a mechanical way instead of in a magical, unscientific way. Like the bending of space-time is pulling the apple towards the floor. How is the bending or the curving of space-time doing anything of the sort? And then you have all these videos.
How can you bend time? That's
not just that. You have all these videos on YouTube, and everybody's they're trying to say that because of the flow of time is creating the force of gravity. Such nonsense. They make zero sense.
That one doesn't actually make sense. Like,
nothing.
That's not even like in the theory of relativity.
What?
YouTube. Yeah, that one is not even the theory of relativity. That's just YouTube being YouTube.
but
I don't think Einstein ever said the.
No, but these are no. So PBS Spacetime said that, and PBS Spacetime, that guy, he's a physics professor. He teaches.
Yeah, but that's weird because I don't think that's even assuming general relativity. I don't think that's correct at all.
Look, what do you want me to say? Of course I disagree. Of course it's nonsense. Of course it's unscientific mumbo jumbo. But even Sabine Hossenfeld, I mean, they all don't understand GR nor SR nor quantum mechanics, but they all make millions, Meanwhile, we're here sitting talking. We understand everything, but we're not making a dime off this.
Yeah, I mean that's how the world is, really.
Exactly.
I think that's how it's always been.
Yeah.
I don't think it's ever very different from that. Like look at.
No, but
for
that's
example,
why, No, but that's why it's so important for me to. Today, I was able to prove Einstein's postulate. So I think we should submit a paper that we want to correct Einstein, at least on this point. We can
it's
prove
going to be very difficult to do that.
No, No, I don't think so. I think we should be
I
able.
mean, you can submit a paper, but it's never going to be like accepted by anyone.
Why not? It's a mathematical proof. I'm proving something that Einstein assumed. By the way, he also assumed that the laws of nature, the laws of physics don't change, which is also nonsense. You don't need that if you just do wave mechanics. So and since the ether is a liquid, special relativity is just wave mechanics. We don't need to say anything about the laws of physics and nonsense like that. So I think we should write a paper. I started writing a paper. I think we should concentrate on a minimalist paper. Just this point, just the proof that I did today, that any moving observer in a liquid will measure a constant speed of waves, where the clocking is done by a clock based on the waves. So thereby making special relativity just wave mechanics. It's not a theory, it's just wave mechanics.
That's very similar to Dialect's video, yes.
Very similar, except for they didn't do it. They didn't prove that that the speed of the wave is a constant. They didn't do that.
Yeah, I mean that's not bad. That's a good paper that could be accepted.
Right.
Question is if you're going to go further than that. They will come after you.
So I'm a minimalist. I don't want to write a paper that's going to get rejected because it has so many things that I don't want to. It's enough. Like once we get our foot through the door, just put the foot through the door. If we get one paper in correcting Einstein, you don't need to do anything else. Just a tiny bit. We're just going to correct Einstein. This little postulate, it's not necessary. We actually have proof for this postulate. If you assume ether as a liquid, it's going to blow their brains. It's going to blow their minds. I'm sorry. They're going to fight it tooth and nail. But if it's a minimalist paper, just a tiny proof, they're going to have to accept it. And it's going to break all of physics. It will break all.
Yeah, they're going to have to accept it, but then they will have like a million excuses as to why.
I don't care. Then we write the second paper. Then we write the third paper. Every time you write a tiny paper that is, making one tiny point and nothing else, and don't say anything, because these people are making a lot of money. And they don't want to be made to look like idiots. So you need to be very sensitive. Because if you make them look like idiots and you're risking them losing their income, they're going to come after you. And they're going to say that, all the worst things you want. They'll say that, I don't want to say what they're going to say. Of course, they're going to say terrible things about you. That you're a right-winger and you support Trump. They're going to come after you like, they know how to do that. Trust me. That's
going to be a bit hard.
They're going to say you're a global warming denier and you're a this denier and that. They're gonna give you the whole 9 yards. So you got to be very, very, very minimalist in this paper. Just this postulate, Einstein, he said that it's a postulate. It's a conjecture that they turned into a postulate. Not necessary. Here is the proof why it's not necessary. If you just assume a liquid ether through which light travels, through which, just a minute, And here is the proof. Thank you. A one-page paper, just reference to Einstein.
I wonder if there's that's not already been done.
So that's what you came in exactly as I'm looking at lectures. I'm trying to see if anyone ever mentioned it. I already did a lot of research.
No, in lectures you won't find it, but I'm talking about papers especially from the time when Einstein was doing his stuff. Because there were people who were convinced of that.
But in Einstein would have retracted. If someone would have written a paper, then people would have reacted to it. I searched Google.
I don't know.
Okay, you should go shopping. When you come back, we can continue doing
Yeah,
this search to see if, and I think we should start writing a very short paper, and have it submitted.
yeah, we can do that.
We can submit it to archive. So, you don't need to submit it to a magazine. Just submit it to archive, to the archive server, and yeah, and then put it on X, on Twitter, and make a YouTube video about it, and start talking about it and ask, Avi Loeb, Professor Avi Loeb,
Yes, yes, the guy of the alien stuff.
the Oumuamua guy. So I actually contacted him. We have an email, like back and forth email. He's very easy to reach. So I think we should maybe he wants to be a co-writer in this paper. We can maybe him, or it could be really interesting. Maybe we could get him. We should think who else might want to join us as a collaborator. This could be really nice.
Yeah, if he wants to. I don't know. I think it's a good thing to try, just to be really simple and be really careful with the maths and just do everything right.
Yeah.
If we do that, that's okay.
Yeah, and then look, we can follow the rubber ducky model. So I have a rubber ducky model that I started working with, and everything should be based on the rubber ducky model. To make just a little bit fun of them, just to a little bit make fun of them, but also to show that we can teach it to children. We can teach it in a lab. We can actually produce these, because I believe that science must be a mechanical contraption. Any scientific theory must be a mechanical contraption. So this rubber ducky will do everything. It will have the wave sensor built in. It will have the clocking, ticking built. Everything would be built in. So you could sell this rubber ducky online. We could even sell the rubber ducky online and make money. Produce the rubber ducky.
Yeah.
And we'll call it the rubber ducky model, the rubber ducky wave mechanics model, and we can and do all of special relativity using the rubber ducky model, and actually conduct experiments with the rubber ducky and show that all of relativity. I mean, time dilation is obvious. Length contraction, I didn't look at. I need to look at it. Have you ever looked at length contraction?
It works as well.
Okay, so
I mean, it's just length contraction and time dilation. Length contraction is just a consequence of time dilation, basically. There's nothing special about it. And Dialect has a video on that that explains length contraction.
Length contraction. Wait, he explains length contraction in the sound clock?
Yeah.
No, not with the
in the sound clock. In the sound clock, he does explain partially why.
Very little. He doesn't go into the equation. He doesn't show the equations of length contraction. So I want to be, but
you can kind of deduce them.
Yeah, I need to study it. I still have not done that. That's like a whole, and then I need to look at the momentum, relativistic momentum. What do you know about that? Why do we get relativistic momentum?
I don't know.
I think so. I have an intuition because of length contraction. So you're getting more and more mass at one, right? That's the reason why you get electromagnetic effects. I mean, magnetism is an effect of length contraction. So for the same reason,
they say that.
What?
They say that. I think that's kind of how the official explanation goes.
No.
But magnetism is probably a bit more complicated than that.
No. You don't need. No. Everything works. Einstein did a good job. From the assumptions, he did a good job. Just the assumptions are superfluous. He says the ether is superfluous. So we need to say no. His assumptions are superfluous. The ether is a mechanical model, and his theory is unscientific. And now we're going to present a scientific version that does not contradict Einstein at all, doesn't contradict any physics, but it's a scientific version So it's a mechanical version. Therefore, it's it's a simpler. Obviously, it's
And
much simpler.
if someone comes and says that the Michelson-Morley experiment proved that data doesn't exist, you will just say that it's moving vertically. Okay. Yeah.
No. I would say that I would have predicted a null result based on a 1 meter arm using, even a laser, even a red laser. A 1 meter arm will give you a null result vertically or
That
horizontally. It doesn't matter. You need even a 2 kilometer arm, about at least a 1 kilometer, I would say 600-meter arm with a vertical test, or I think like a couple of kilometers with a horizontal test, or with gamma rays. Maybe you can do it with like microwaves or X-rays. You can like 1 nanometer, maybe a 1 meter apparatus should do horizontally or vertically.
Yeah, but you can detect like very small differences within the fringes.
I don't know.
You can
Like,
detect.
I'm looking.
You can do it. You should check the live stream that I sent you with Shiva. I think he goes through that there was a small result on the Michelson-Morley experiment, very very small. They just didn't consider it enough.
So I'm looking for at least one complete wavelength. So one wavelength over 90 degrees.
Yeah, I understand. I understand what you're looking at, but you can measure less than that. That's possible.
Look, if it's statistically significant, then fine. I mean, I guess look, if your equipment, because you can have like an if you're using ultraviolet light, then you can detect electricity, and then you can be much more sensitive with a scope, with an oscilloscope. So you might be able to get extreme sensitivities, and then you might get statistically significant even with a 1 meter arm, horizontal arm. Maybe, I don't know. I need to see, because I'm just
you can get a little bit of a result. The thing is, they predicted a very high result because of because I think that the ether is the Earth going around is going around the ether, and the ether is stationary and the Earth is rotating.
That's not.
They they predicted it all like that. So
no, that's unscientific. No. So what? So Michelson is guilty of conducting an unscientific experiment. That he's guilty of, and for that he paid he got a Nobel Prize, but he died thinking that he failed. And the failure is that he did not go through the calculations properly. I don't think he should. I mean, any way you look at it, he should have expected a null result. I don't know what he was expecting. So
no, it was. I'm trying to explain. Like the idea is that imagine the ether is stationary and the Earth is rotating. So we predicted that the speed of the rotation of the Earth would be seen in the experiment.
Wait, Michelson?
And then, but yeah, he predicted something like that, and then he also predicted that that over the course of the year this would change.
No.
Because of the position of the Earth.
No.
He predicted some stuff like that.
That's nonsense. That's not scientific. He had to come first with a scientific theory, and then a prediction, and then a test. You can't just nilly-willy run around. That's why he destroyed his life. Because he ran too fast to conduct this experiment. So sometimes you pay dearly for your mistakes. He died thinking he's a failure because he didn't slow down. You have to follow Bacon's algorithm of science. Otherwise, you're going to ruin your life and everybody else is in the process. He destroyed the world. Michelson he gave us 100 years of scientific dark ages because of his mistake.
I mean, I wouldn't put all the blame on him.
I would put a lot of it on him because he conducted.
I mean, people need to question things.
Look, he conducted the experiment. I mean, other people conducted this experiment, and he got a null result. So everybody thinks That he got a null
Hey,
result. Hi, Lily.
what's up?
So, so everybody thinks he got a null result, and everybody trusts. See, people trust you as an expert. You cannot play with this trust that the public puts in the hands of scientists. Once you
Yeah, but that's what I'm saying. It didn't really get the null result. Like he got the result. It's just thought that
that he should not,
even his assumption,
then he should
the
not have,
result wasn't.
then he should not have accepted the Nobel Prize. He got a Nobel Prize for the null result.
I think he should not have said that he got a null result. That's the thing.
Fine,
Because he
whatever.
got the result.
Look, either way,
That's
the
he should
idea,
have said, "Oh, I got the result." So
the idea,
it's an unexpected result.
the idea that the
So,
ether changes direction through the year is complete nonsense. That's unscientific. What do you? Why the ether is not?
yeah, but that's what I'm trying to tell you. That's like the general thing that that people think about. That people think. That's how people think it works.
Then that's unscientific. That's magical thinking. So if that's thought, then that it's good that he was punished. He died.
Well, but it's not just him. It's like everyone in the scientific community thinks that's the theory of the ether.
So one of the papers we need to write is what is proper science and why. Like I need to explicate this. Anyway, when are you going shopping?
Yeah, probably go right now. So, all right, check the experiment, the Stern whatever experiment.
No, it's
I'll see you
useless.
later.
I know it, but I don't have enough information yet. I need to do a lot of homework before then.
Okay.
Anyway, I'll see you later, man.
See you.
Okay, bye.
Bye. Nice talking to you.
Yeah, nice talking to you. Bye. I'm waiting for you to come back so we can continue talking. Bye. All right. Yeah. Okay.
Wait, how do I leave? How do I leave this thing?
How do you leave? You have to go back to general. Go back to general.
Oh, it's here. Oh, wait.
And you need to click the red button twice. Once to leave the blackboard. First, go to general. Go to the general VC. I mean, go to the VC. The audio. And then
okay, so it's here and it's here. Okay, so
exactly.
I've seen it. Here.
Exactly. All right, bye. All right. Okay, we've been here for 3 hours. Let's cut the stream, and we'll come back later and do some more research. Okay, bye everyone.